Light travels at 299,792,000 kilometers per second. This isn't just incredibly fast, it's the very foundation upon which our entire reality is built. Every equation in physics, every measurement of time and space, every understanding of energy and matter depends on this one unchanging number. Scientists call it C, and it's woven into the fabric of existence itself. But tonight, we're going to explore something that should be impossible. What if this most fundamental constant, this pillar of reality, suddenly changed overnight? What if the speed of light that has remained constant since the beginning of time itself decided to become something else entirely? Would the universe survive? Would we survive? Or would reality itself simply cease to exist as we know it? This isn't just a question about physics. It's a question about the very nature of existence. Because when we dig deep enough into the laws that govern our cosmos, we discover that nothing exists in isolation. Every force, every particle, every law of nature is interconnected in ways that would make a single change ripple through everything we thought we knew about the universe. The speed of light isn't just about how fast photons travel through space. It's about time itself, about the relationship between energy and matter, about the structure of atoms and the behavior of black holes. It's about why you can't travel faster than light, why time slows down when you approach that speed, and why the universe has the particular shape and age that it does. Picture standing in a vast cosmic cathedral where every pillar, every arch, every stone depends on this one fundamental measurement. Pull out that single stone, change that one number, and the entire structure doesn't just shake, it collapses into something unrecognizable. The laws of chemistry would rewrite themselves. The forces that hold atoms together would shift. The very concept of distance and duration would transform into something alien. Throughout history, humans have measured this speed with increasing precision. From the first crude attempts to time light bouncing between mirrors to the most sophisticated modern experiments, we've found the same answer every time. Light never speeds up, never slows down, never changes. It's as reliable as gravity, as constant as the passage of time itself. Yet in our thought experiment tonight, we're going to shatter that reliability. We're going to imagine waking up in a universe where the impossible has happened, where the speed of light has changed, and with it, everything we thought we knew about reality. The journey ahead will take us through collapsing physics, failing technology, transformed time, and ultimately to the question of whether humanity itself could survive in such a radically altered cosmos. So as we embark on this journey into the impossible, remember that we're not just asking what would happen if light moved differently. We're asking what would happen if the fundamental rules of reality rewrote themselves while we were sleeping. The answer might be more terrifying and more beautiful than we could ever imagine. To understand what would happen if the speed of light changed, we first need to understand just how deeply this constant is embedded in the very structure of reality. The story begins centuries ago, when humans first began to wonder if light had a speed at all. Galileo Galilei, in the early 1600s, attempted the first crude measurement. He and an assistant stood on hilltops miles apart, flashing lanterns at each other, trying to time the delay. Of course, human reflexes were far too slow to detect something moving at nearly 300 million meters per second. But Galileo's failure was still progress, because it suggested that light moved faster than anything humans had ever encountered. The breakthrough came in 1676, when Danish astronomer Ole Rømer noticed something peculiar about Jupiter's moon Io. The moon seemed to disappear behind Jupiter at slightly different times depending on whether Earth was moving toward or away from Jupiter in its orbit. Rømer realized he was seeing light itself taking different amounts of time to reach Earth across the varying distances. This gave humanity its first real measurement of light speed, and it was staggeringly fast. Over the following centuries, scientists refined their measurements with increasingly sophisticated methods. In 1849, Hippolyte Fizeau used a spinning gear wheel to chop up a beam of light, measuring how fast the gear had to spin to block the returning light. Léon Foucault improved on this with rotating mirrors, achieving unprecedented precision. By the late 1800s, Albert Michelson had pushed the accuracy to within 1% of the modern value using interferometry, a technique so precise it could detect changes smaller than the width of an atom. Each of these measurements revealed the same startling truth. Light always traveled at the same speed, regardless of its source or color. Red light, blue light, infrared radiation, X-rays, radio waves. They all moved at identical speeds through the vacuum of space. This wasn't just a coincidence. It was a fundamental property of the universe itself. The precision of these measurements grew exponentially. By the 1920s, Michelson and his colleagues had refined their techniques to measure the speed of light to within a few parts per million. Modern measurements using laser interferometry and atomic clocks have pushed this precision to 15 decimal places. We now know the speed of light to be exactly 299,792,458 meters per second. But it wasn't until Albert Einstein arrived on the scene in 1905 that we truly understood what this speed meant. Einstein's special theory of relativity revealed that the speed of light wasn't just fast, it was the cosmic speed limit. Nothing with mass could ever reach it, and nothing could ever exceed it. More importantly, Einstein showed that this speed was the same for all observers, regardless of how fast they were moving. This constancy of light speed seemed to violate common sense. If you're driving toward an oncoming car, the relative speed between you increases. But if you're traveling toward a beam of light, even at 99% of light speed, the light still approaches you at exactly c. This paradox forced Einstein to completely reimagine space and time. This revelation transformed our understanding of space and time. Einstein showed that as you approach the speed of light, time itself slows down relative to stationary observers. Travel at 99% of light speed, and time crawls to a near standstill. This isn't science fiction. It's been measured countless times in particle accelerators and GPS satellites. Muons created in the upper atmosphere should decay long before reaching Earth's surface, but because they're moving at nearly the speed of light, time dilation allows them to survive the journey. The mathematics of time dilation is elegant in its simplicity. The time dilation factor is 1 divided by the square root of 1 minus v squared over c squared. At everyday speeds, this factor is essentially 1, meaning no noticeable time dilation. But as you approach the speed of light, this factor grows toward infinity. At 99.9% of light speed, time slows by a factor of 22. What feels like 1 hour to the traveler appears as 22 hours to a stationary observer. The speed of light also revealed the famous equation E equals mc squared. This simple formula tells us that mass and energy are interchangeable, and the speed of light squared is the conversion factor. A tiny amount of mass contains an enormous amount of energy, precisely because c squared is such a huge number. This is why nuclear reactions are so powerful, and why the sun can shine for billions of years by converting just a small fraction of its mass into energy. Consider the implications. A single gram of matter, if completely converted to energy, would release the equivalent of 21,000 tons of TNT. The speed of light squared, that enormous number of 9 times 10 to the 16th meters squared per second squared, is what makes this possible. Every nuclear power plant, every star in the sky, every fusion reaction depends on this relationship between mass, energy, and the speed of light. The sun converts about 4 million tons of mass into energy every second, yet it has enough mass to continue this process for another 5 billion years. This is the power hidden in E equals EMC squared. The speed of light isn't just about motion, it's about the fundamental equivalence of mass and energy that powers the universe itself. But Einstein didn't stop there. His general theory of relativity, published in 1915, showed that the speed of light also governs the geometry of space-time itself. Massive objects warp the fabric of space and time, and this warping is what we experience as gravity. The equations that describe this warping are filled with factors of c, connecting the speed of light to the fundamental force that holds planets in orbit and keeps our feet on the ground. In Einstein's field equations, the speed of light appears in multiple places, binding together the curvature of space-time with the distribution of matter and energy. The equation relates the geometry of space-time to the stress-energy tensor, and the speed of light acts as the conversion factor between space and time coordinates. Without c, there would be no way to compare a meter of distance to a second of time. Gravitational waves, ripples in space-time itself, propagate at exactly the speed of light. When two black holes collide billions of light years away, the distortions they create in space-time reach us at precisely c, allowing us to detect these cosmic catastrophes with instruments like LIGO. These waves carry energy away from the colliding objects, and the power radiated depends on the speed of light raised to the fifth power. The speed of light is also intimately connected to other fundamental constants of nature. The fine structure constant, which governs the strength of electromagnetic forces, depends directly on the speed of light. This constant, approximately 1 divided by 137, determines how strongly electrons are bound to atomic nuclei, how bright stars shine, and how stable matter itself can be. Change c, and you change the fine structure constant, potentially making atoms impossible to form. The fine structure constant is dimensionless, meaning it has no units. It's simply a number that emerges from the combination of the elementary charge, Planck's constant, and the speed of light. This constant determines the strength of electromagnetic interactions, governing everything from the colors of light emitted by atoms to the stability of chemical bonds. The relationship goes deeper still. The Planck length, roughly 10 to the negative 35 meters, represents the smallest meaningful distance in the universe. The Planck time, about 10 to the negative 43 seconds, is the shortest meaningful duration. The Planck energy, equivalent to the energy of a lightning bolt concentrated into a space smaller than a proton, represents the scale at which quantum effects and gravity become equally important. All of these fundamental units depend on the speed of light, Planck's constant, and the gravitational constant working together. These Planck units aren't arbitrary. They represent the natural scales of the universe, the fundamental granularity of space and time. The Planck length is the distance light travels in one Planck time, and the Planck energy is the energy of a photon with wavelength equal to the Planck length. Change the speed of light, and you change these fundamental scales, potentially making the universe unrecognizable at the quantum level. In quantum mechanics, the speed of light appears everywhere. Photons, the particles of light, are massless and always travel at c. The uncertainty principle, which limits how precisely we can know both the position and momentum of a particle, depends on relationships involving the speed of light. The quantum vacuum itself, the empty space between particles, bubbles with virtual particles that pop in and out of existence at rates determined by c. The Dirac equation, which describes the behavior of electrons and other spin 1/2 particles, contains the speed of light as a fundamental parameter. This equation predicts the existence of antimatter, and the energy scale for particle creation depends directly on c. In quantum field theory, the speed of light sets the scale for how quickly information and causality can propagate through the quantum vacuum. Modern physics has revealed that the speed of light emerges from deeper symmetries in the universe. It's not an arbitrary number that could be anything. It's a consequence of the fundamental structure of space-time, emerging from the very geometry of reality. The speed of light is related to the symmetries that govern how space and time transform when we change our reference frame. These symmetries, known as Lorentz transformations, are built into the very fabric of space-time. The Lorentz transformations show how space and time coordinates change when you switch between different reference frames, moving at constant velocities. These transformations depend critically on the speed of light, which acts as the universal scale that connects space and time. Without c, there would be no way to relate distances to durations, no way to understand how motion affects the measurement of space and time. The electromagnetic force itself depends on the speed of light. Light is an electromagnetic wave, and the speed at which these waves propagate depends on the fundamental properties of space. The permittivity and permeability of free space, constants that determine how electric and magnetic fields behave, are related to the speed of light by a simple equation. Change the speed of light, and you change the strength of electric and magnetic fields, potentially making chemistry impossible. Maxwell's equations, which govern all electromagnetic phenomena, contain the speed of light as a fundamental parameter. These equations predict that changing electric fields create magnetic fields, and changing magnetic fields create electric fields. The speed at which these electromagnetic waves propagate is determined by the properties of space itself, and that speed is c. The forces that hold molecules together, that allow DNA to replicate, that enable the complex biochemistry of life, all depend on electromagnetic interactions that are calibrated to the current speed of light. The strength of the hydrogen bond, the stability of the double helix, the rates of chemical reactions, all depend on electromagnetic forces whose strength is determined by the speed of light. Even the expansion of the universe is intimately connected to the speed of light. The cosmic microwave background radiation, the afterglow of the Big Bang, has traveled at the speed of light for over 13 billion years to reach us. The Hubble constant, which measures how fast the universe is expanding, is calibrated in units that depend on the speed of light. Change c, and our understanding of cosmic distances, the age of the universe, and the fate of everything we can see would need to be completely rewritten. The cosmic microwave background provides a snapshot of the universe when it was only 380,000 years old. The temperature variations in this radiation tell us about the density fluctuations that would eventually grow into galaxies and stars. The angular size of these fluctuations depends on how far light could travel in the early universe, a distance determined by the speed of light multiplied by the age of the universe at that time. Stellar nucleosynthesis, the process by which stars forge heavy elements from hydrogen and helium, depends on the speed of light through the mass-energy relationship. The binding energy of atomic nuclei, the energy released in nuclear fusion, the lifetime of stars, all depend on E equals mc squared. Change c, and you change the energy available from nuclear reactions, potentially making star formation impossible. The speed of light also appears in the equations that govern black holes. The Schwarzschild radius, the size of a black hole's event horizon, depends on the speed of light squared. The Hawking radiation emitted by black holes has a temperature that depends on the speed of light. Even the information paradox, one of the deepest mysteries in modern physics, hinges on whether information can escape from black holes at the speed of light. This is why our thought experiment is so profound. We're not just imagining a world where cars drive faster or planes fly differently. We're imagining a world where the fundamental constants that give rise to chemistry, biology, gravity, and even time itself have been rewritten. The speed of light is the thread that holds the tapestry of physics together. And if we pull on that thread, the entire fabric of reality might unravel in ways we're only beginning to understand. What would happen if this constant, this pillar of existence, suddenly changed overnight? The answer will take us on a journey through the collapse of everything we thought we knew about the universe. Every equation would need to be rewritten, every measurement recalibrated. every understanding of how reality works fundamentally altered. The speed of light isn't just a number, it's the foundation upon which all of physics rests. Imagine waking up tomorrow morning to a universe where the speed of light has changed overnight. Perhaps it's now half its original value, or maybe it's doubled. The moment this fundamental constant shifts, reality itself begins to unravel in ways that would make the most catastrophic disasters in human history seem like minor inconveniences. The first victim would be energy itself. Einstein's famous equation E equals mc squared tells us that even tiny amounts of matter contain enormous energy, but only because c squared is such a vast number. If the speed of light suddenly dropped to half its current value, c squared would become 4 times smaller. Every atom in the universe would instantly contain 4 times less energy than it did the moment before. This isn't just a theoretical curiosity. The binding energy that holds atomic nuclei together depends directly on this mass-energy relationship. Protons and neutrons are bound together by the strong nuclear force. But the energy scale of this binding is set by E equals mc squared. If C suddenly decreased, the binding energy of every nucleus would drop proportionally. Atoms that were stable for billions of years might suddenly find themselves with too much mass for their reduced binding energy to hold together. The Sun, our life-giving star, would face an immediate crisis. Nuclear fusion in the Sun's core converts hydrogen into helium, releasing energy according to the mass-energy equivalence. 4 hydrogen nuclei, with a combined mass of about 6.69 times 10 to the negative 27 kilograms, fuse to create 1 helium nucleus with a mass of 6.64 times 10 to the negative 27 kilograms. The difference, about 0.7% of the original mass, becomes energy. But if Cc changed overnight, this energy release would change proportionally to c squared. A 50% reduction in the speed of light would mean fusion reactions would release only 25% of their previous energy. The Sun's core, which has been in perfect balance between gravitational collapse and radiation pressure for 4.5 billion years, would suddenly find itself generating insufficient energy to maintain that balance. The consequences would unfold rapidly. With reduced radiation pressure, gravity would begin to win the eternal battle at the Sun's heart. The core would start to contract, heating up as gravitational potential energy converts to thermal energy. This might temporarily increase the fusion rate, but it would also destabilize the delicate equilibrium that has kept our star shining steadily for eons. Meanwhile, photons themselves would undergo a dramatic transformation. Light carries energy, and the energy of a photon depends on its frequency through Planck's equation E equals h times f, where h is Planck's constant and f is frequency. But photons also travel at the speed of light, and there's a fundamental relationship between frequency, wavelength, and the speed of light. C equals f times lambda, where lambda is wavelength. If the speed of light changed but the fundamental properties of photons remained the same, their frequencies and wavelengths would have to adjust to maintain this relationship. A photon that was red light before the change might suddenly become infrared radiation. What appeared as visible light might shift into the ultraviolet or infrared ranges. The entire electromagnetic spectrum would compress or expand, fundamentally altering how we perceive the world around us. But the changes would go far deeper than perception. The energy of electromagnetic radiation depends on frequency, so shifting the spectrum would change the energy content of all light. Plants that have evolved to harvest energy from specific frequencies of sunlight would suddenly find themselves trying to photosynthesize with radiation of completely different energies. The delicate chemical processes that power all plant life might simply stop working. The quantum world would experience its own form of chaos. Quantum mechanics is built on the foundation of fundamental constants. and the speed of light appears throughout the mathematical framework that describes atomic and subatomic behavior. The fine structure constant, which determines the strength of electromagnetic interactions, depends directly on the speed of light. Change c, and you change how strongly electrons are bound to atomic nuclei. This isn't a minor adjustment. The fine structure constant determines the energy levels of electrons in atoms, which in turn determines the colors of light that atoms can absorb and emit. Every element has a unique spectroscopic signature, a fingerprint of light that allows us to identify what atoms are made of, even across vast cosmic distances. Change the speed of light, and these signatures would shift dramatically. Hydrogen, the simplest and most abundant element in the universe, would no longer emit its characteristic red line at 656 nanometers. The entire periodic table would need to be rewritten as electron energy levels shifted throughout all atoms. Chemical bonds, which depend on the electromagnetic forces between electrons, would weaken or strengthen unpredictably. The changes would cascade through chemistry like a house of cards collapsing. Molecules that were stable for billions of years might suddenly decompose as their bonds weaken beyond the breaking point. Water molecules, held together by hydrogen bonds that depend on electromagnetic forces, might become unstable. The very liquid that makes life possible could cease to exist in its familiar form. DNA, the molecule that carries the genetic information for all life on Earth, relies on precise electromagnetic interactions between its bases. The double helix is held together by hydrogen bonds, weak electromagnetic forces that are perfectly calibrated to allow the molecule to unzip for replication while remaining stable enough to preserve genetic information. Change the strength of electromagnetic interactions, and DNA might either become too stable to replicate or too unstable to preserve information. Proteins, the molecular machines that carry out most biological functions, depend on precise folding patterns determined by electromagnetic interactions between amino acids. These folding patterns have been refined by billions of years of evolution to create enzymes, structural proteins, and signaling molecules that make life possible. Alter the electromagnetic interactions, and proteins might fold into entirely different shapes, losing their function and potentially becoming toxic to the cells that created them. Even the forces that hold matter together would face disruption. The electromagnetic force, one of the four fundamental forces of nature, would change strength in proportion to the change in the speed of light. This force is responsible for all chemical bonds, all molecular interactions, and all biological processes. A universe with a different speed of light would literally be held together by different rules. But perhaps most dramatically, space-time itself would become unstable. Einstein's general relativity shows us that the speed of light is woven into the very geometry of space and time. The field equations that describe how matter and energy curve space-time contain factors of c in multiple places. Change the speed of light, and you change the fundamental relationship between matter, energy, and the curvature of space-time. Gravitational waves, ripples in space-time that propagate at the speed of light, would suddenly travel at a different speed. This might seem like a minor change, but it would fundamentally alter how quickly gravitational effects can propagate through the universe. Currently, if the sun suddenly disappeared, Earth would continue orbiting for about 8 minutes, the time it takes light to travel from the sun to Earth. This is because gravitational effects, like light, propagate at c. If the speed of light changed, this gravitational speed limit would change with it. The universe would either become more tightly connected, with gravitational effects propagating faster, or more loosely connected, with gravitational influences taking longer to travel between objects. Either change would disrupt the delicate gravitational balance that keeps planets in stable orbits and galaxies bound together. The cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space, would undergo dramatic changes. This radiation has been traveling through the expanding universe for over 13 billion years, and its properties depend critically on the speed of light. Change c, and the temperature, frequency distribution, and intensity of this background radiation would all shift. This cosmic background radiation is currently at a temperature of about 2.7 Kelvin, just above absolute zero. But if the speed of light changed, the energy of this radiation would change proportionally. The universe might suddenly be flooded with higher energy radiation, potentially sterilizing any remaining life, or the background radiation might become so low energy that it would no longer play its current role in cosmic evolution. Black holes, those gravitational monsters where space-time curvature becomes infinite, would face their own crisis. The event horizon of a black hole, the boundary beyond which nothing can escape, has a size determined by the Schwarzschild radius. This radius depends on the speed of light squared, so changing c would immediately change the size of every black hole in the universe. If the speed of light increased, black holes would shrink. If it decreased, they would grow. Either change would have catastrophic effects on anything orbiting near a black hole. Material that was safely outside the event horizon might suddenly find itself trapped forever, or conversely, material that was trapped might suddenly find itself able to escape. The Hawking radiation emitted by black holes also depends on the speed of light. Stephen Hawking showed that black holes emit radiation due to quantum effects near the event horizon, and the temperature of this radiation is inversely proportional to the black hole's mass, but also depends on fundamental constants including c. Change the speed of light, and the rate at which black holes evaporate would change dramatically. Perhaps most fundamentally, the very concept of causality would be threatened. The speed of light isn't just about how fast light travels. It's the cosmic speed limit that ensures cause precedes effect. Nothing can travel faster than light because doing so would allow information to travel backward in time, creating paradoxes that would make the universe logically inconsistent. If the speed of light suddenly changed, this speed limit would change with it. Particles or signals that were previously traveling below the cosmic speed limit might suddenly find themselves exceeding it, potentially violating causality. The carefully ordered sequence of cause and effect that makes the universe comprehensible might collapse into chaos. The quantum vacuum itself would be affected. Empty space isn't really empty, but seethes with virtual particles that pop in and out of existence according to the uncertainty principle. The energy scale and time scale of these quantum fluctuations depend on fundamental constants, including the speed of light. Change c, and the very nature of empty space would change. These virtual particles play crucial roles in many physical processes. They mediate forces between particles, contribute to the energies of atoms, and even affect the structure of space-time itself. Alter their behavior by changing the speed of light, and the foundations of particle physics would crumble. What we're describing isn't just a disaster, it's the complete breakdown of physical law as we understand it. Every equation would need to be rewritten, every measurement recalibrated, every understanding of how the universe works fundamentally altered. The speed of light isn't just a number in physics textbooks, it's the foundation upon which all of reality rests. Pull out that foundation, and everything we know about existence collapses with it. While the universe itself struggles to maintain coherence under new physical laws, human civilization would face its own immediate and devastating collapse. Every piece of technology we depend on, from the smartphone in your pocket to the power grid that lights our cities, operates according to principles that assume the speed of light remains constant. Change that fundamental constant, and our technological civilization doesn't just falter, it crashes completely. The first systems to fail would be our most precise instruments, atomic clocks, which form the backbone of global navigation and telecommunications, depend on the exact frequency of electromagnetic radiation emitted by cesium atoms. These clocks are so accurate, they would gain or lose less than 1 second over 300 million years. But their precision comes from measuring electromagnetic transitions that depend directly on the fine structure constant, which depends on the speed of light. The moment C changes, every atomic clock on Earth would begin running at a different rate. The cesium atoms that define our standard second would suddenly emit radiation at a frequency that no longer matches our definition of time. GPS satellites, which depend on atomic clocks accurate to within billionths of a second, would immediately begin providing incorrect location data. The Global Positioning System works by measuring the time it takes radio signals to travel from satellites to receivers on Earth. The system must account for both special and general relativistic effects, including time dilation, caused by the satellite's motion and the weaker gravitational field they experience. All of these calculations assume a specific value for the speed of light. Change C, and every GPS calculation becomes wrong. But the problem goes far deeper than navigation errors. Modern civilization runs on a foundation of precisely synchronized time. Every computer network, every financial transaction, every telecommunication system depends on devices agreeing on what time it is. Cell phone towers synchronize their signals using GPS time. Internet routers coordinate data transmission using atomic clock references. The electrical power grid balances supply and demand using timestamps accurate to microseconds. When atomic clocks begin running at different rates, this synchronized foundation crumbles. Cell phone networks would lose the precise timing needed to coordinate signals between towers. Calls would drop, data transmission would become unreliable, and entire networks might go dark as towers fail to coordinate their transmissions. The internet itself would fragment. Data packets traveling between servers rely on precise timing to ensure they arrive in the correct order and can be reassembled into coherent messages. Router networks use timing protocols that depend on synchronized clocks to manage traffic flow and prevent congestion. As these timing references drift apart, the internet would break into isolated islands of connectivity. Financial markets, which execute millions of trades per second based on precise timestamps, would face immediate crisis. High-frequency trading algorithms that buy and sell stocks in microseconds depend on all participants agreeing on the exact time of each transaction. When clocks begin running at different rates, it becomes impossible to determine the order of trades, potentially invalidating entire markets. Electronic devices themselves would face fundamental problems. Semiconductors, the foundation of all modern electronics, operate according to quantum mechanical principles that depend on the electromagnetic properties of materials. The band gaps that determine whether a material is a conductor, semiconductor, or insulator depend on electron energy levels, which depend on electromagnetic interactions, which depend on the speed of light. Silicon, the element that powered the digital revolution, has precisely the right electronic properties to make useful semiconductors. But these properties depend on the fine structure constant, which would change if C changed. Silicon chips might suddenly become insulators, unable to conduct the electrical signals that make computation possible, or they might become too conductive, unable to switch between on and off states that represent digital ones and zeros. The billions of transistors in a modern computer processor are designed with dimensions measured in nanometers, and their operation depends on quantum tunneling effects that are calibrated to current electromagnetic properties. Change the strength of electromagnetic interactions, and these transistors might stop working entirely, or they might work in completely unpredictable ways. Memory devices would face similar problems. Flash memory stores information by trapping electrons in quantum wells, and the energy required to move these electrons depends on electromagnetic forces. RAM stores data by charging tiny capacitors, and the behavior of these capacitors depends on the electrical properties of the materials from which they're made. change electromagnetic interactions, and computer memory might lose all stored information or become unable to store new data. But even if some electronic devices somehow continue to function, they would face another devastating problem. Electromagnetic radiation, including radio waves, microwaves, and optical signals, would all change frequency as the speed of light changed. Radio transmissions that were perfectly tuned to their receivers would suddenly be broadcasting on the wrong frequency. Television broadcasts would become static. Radio stations would go silent. Satellite communications would fail as ground stations could no longer tune to the frequencies being transmitted from space. The electromagnetic spectrum itself would shift, with what used to be visible light potentially becoming infrared or ultraviolet radiation. Optical fiber networks, which carry most of the world's internet traffic as pulses of light, would face catastrophic failure. These systems depend on the precise timing of light pulses traveling through glass fibers. The speed of light in glass is different from its speed in vacuum, and it depends on the material properties of the glass and the frequency of the light. If the speed of light in vacuum changed, the speed of light in materials would change differently, depending on their optical properties. Light pulses that were carefully timed to arrive at their destination in a specific sequence might arrive scrambled or not at all. The careful engineering that allows multiple signals to travel through the same fiber at different frequencies would break down as the relationship between frequency and propagation speed changed. Laser systems, from the barcode scanners in grocery stores to the precision instruments used in manufacturing, would malfunction. Lasers produce coherent light at specific frequencies, and their operation depends on the energy levels of electrons in the laser medium. Change electromagnetic interactions, and laser frequencies would shift, making them incompatible with the systems designed to use them. Medical equipment would fail in dangerous ways. MRI machines create detailed images of the human body using powerful magnetic fields and radio frequency pulses. The precise frequencies used in MRI are chosen to resonate with hydrogen atoms in the body, but these resonant frequencies depend on electromagnetic properties that would change if C changed. MRI scans might produce meaningless images, or worse, the machines might apply radio frequency energy at the wrong frequency, potentially harming patients. X-ray machines and CT scanners depend on high-energy electromagnetic radiation to create images of internal body structures, change the electromagnetic properties of materials, and X-rays might be absorbed differently by different tissues, making medical imaging unreliable or impossible. Transportation systems would face immediate crisis. Modern vehicles rely heavily on electronic control systems that would be affected by the electromagnetic changes. Engine management computers that precisely control fuel injection and ignition timing would malfunction. Anti-lock braking systems and stability control systems would fail, making vehicles dangerous to operate. Aircraft would face even more severe problems. Modern planes are essentially flying computers, with electronic systems controlling everything from engine operation to flight path management. Navigation systems that depend on GPS would provide incorrect position information. Radar systems used for air traffic control would malfunction as their radio frequencies shifted. The electromagnetic navigation beacons that guide aircraft to airports would broadcast on the wrong frequencies. Landing systems that help pilots touch down safely in poor visibility would fail. Even the radio communications between pilots and air traffic controllers would break down as radio frequencies shifted. Trains and subways that depend on electronic signaling systems would be unable to operate safely. The sensors that detect train positions, the computers that control switching, and the communication systems that coordinate train movements would all malfunction simultaneously. Power grids would face a cascade of failures. Modern electrical systems use sophisticated control networks to balance electricity supply and demand across vast regions. These systems depend on precise timing and communication to coordinate power plants, transmission lines, and distribution networks. As timing references drift and communication systems fail, grid operators would lose the ability to manage power flow. Smart grids that automatically adjust to changing demand would become blind to current conditions. Power plants that automatically start up or shut down based on grid conditions would receive incorrect signals. The result would be blackouts cascading across entire continents as the electrical infrastructure loses the ability to maintain stability. Manufacturing systems would halt. Modern factories depend on computerized control systems to coordinate complex assembly processes. Robotic systems that position components with micrometer precision would lose their accuracy as their sensors and control systems malfunction. Quality control systems that use optical inspection and electronic measurement would provide unreliable results. The global supply chain, which moves goods around the world with precision timing, would collapse. Container ships that navigate using GPS would lose their way. Port facilities that use automated cranes and computerized logistics systems would be unable to load or unload cargo. Just-in-time manufacturing, which depends on components arriving exactly when needed, would break down as transportation and communication systems fail. Even water treatment plants and sewage systems would be affected. These facilities use computerized control systems to monitor water quality, control chemical dosing, and manage flow rates. Without reliable sensors and control systems, cities would lose the ability to provide clean water or safely treat waste. The financial system would face immediate paralysis. Electronic banking systems that process millions of transactions per day would be unable to coordinate with each other. Credit card networks would fail as payment processors lost the ability to communicate with banks and merchants. Automated trading systems would malfunction, potentially causing market crashes that make historic financial crises look minor by comparison. Perhaps most critically, emergency services would lose the ability to coordinate responses. 911 systems that route emergency calls to the appropriate responders would malfunction. GPS systems used by police, fire departments, and ambulances would provide incorrect locations. Radio communication systems used by first responders would fail as frequencies shifted. Hospitals would lose access to electronic medical records, automated medication dispensing systems, and computerized monitoring equipment. Just when populations might need medical care most, the healthcare system would be crippled by technological failures. What we're describing isn't just inconvenience, it's the complete collapse of the technological infrastructure that supports modern civilization. Within hours of the speed of light changing, humanity would find itself thrust back to a pre-electronic age. But without the knowledge, skills, or infrastructure that previous generations used to survive without modern technology. The irony is profound. Our mastery of electromagnetic phenomena allowed us to build a technological civilization of unprecedented complexity and capability. But that same mastery makes us utterly dependent on electromagnetic properties, remaining exactly as they are. Change the speed of light, and the very forces we harnessed to build our modern world become the instruments of its destruction. Beyond the collapse of human technology and the breakdown of familiar physics lies an even more fundamental question. Would the universe itself survive such a dramatic change? The cosmos as we know it exists in a delicate balance of forces, energies, and physical laws that have remained constant for nearly 14 billion years. Change the speed of light, and we're not just altering one number in a physics textbook. We're rewriting the fundamental rules that determine whether stars can shine, whether galaxies can exist, and whether the universe can support any form of complexity at all. The most immediate cosmic casualty would be the structure of atoms themselves. Every atom consists of a nucleus surrounded by electrons, held together by electromagnetic forces whose strength depends directly on the fine structure constant. This constant, approximately 1 divided by 137, emerges from a combination of the elementary charge, Planck's constant, and the speed of light. Change C, and you immediately change the strength of electromagnetic interactions throughout the universe. If the speed of light increased, electromagnetic forces would weaken. Electrons would be less tightly bound to their nuclei, and atoms would become larger and more diffuse. Chemical bonds, which depend on electromagnetic interactions between atoms, would weaken proportionally. The molecules that make up everything from water to DNA would become less stable. Conversely, if the speed of light decreased, electromagnetic forces would strengthen. Electrons would be pulled closer to their nuclei, atoms would shrink, and chemical bonds would become stronger. While this might sound beneficial, it would actually be catastrophic. Chemical reactions depend on bonds being strong enough to hold molecules together, but weak enough to break and reform during reactions. Make electromagnetic forces too strong, and chemistry might grind to a halt. The periodic table of elements would need to be completely rewritten. Each element's properties depend on the energy levels of its electrons, which depend on electromagnetic interactions. Hydrogen, the simplest atom with just 1 proton and 1 electron, would no longer emit its characteristic spectral lines at the familiar wavelengths. The Lyman series, the Balmer series, and all the other spectroscopic signatures that allow us to identify hydrogen across the cosmos would shift to entirely different frequencies. The hydrogen 21 centimeter line, used by radio astronomers to map the structure of our galaxy and distant galaxies, would no longer be at 21 centimeters. This spectral line, produced when the electron in a hydrogen atom flips its spin, has been our window into the distribution of neutral hydrogen throughout the universe. Change the electromagnetic interactions, and this line would shift to a completely different wavelength, potentially making it impossible to detect with existing instruments. Carbon, the foundation of all known life, might no longer be able to form the 4 stable bonds that make complex organic chemistry possible. The carbon-carbon bonds that create the backbone of biological molecules depend on precise electromagnetic interactions between electrons in different atoms. Change those interactions, and carbon might become chemically inert or hyperactive, either way making organic chemistry impossible. The unique properties that make carbon so special for forming complex molecules come from its electron configuration. Carbon has 4 electrons in its outer shell, allowing it to form 4 covalent bonds with other atoms. But the strength and geometry of these bonds depend on electromagnetic forces. Alter those forces, and carbon might prefer to form fewer bonds, making long-chain molecules impossible. Or it might form too many bonds, making it impossible for carbon compounds to be flexible enough for biological functions. Oxygen, essential for respiration and combustion, would face similar problems. The double bond in oxygen molecules and the polar nature of water molecules both depend on electromagnetic forces calibrated to current values. Alter these forces, and oxygen might no longer support combustion, or water might no longer have the unique properties that make it essential for life. Water's remarkable properties emerge from the precise electromagnetic interactions between hydrogen and oxygen atoms. The hydrogen bonds that give water its high boiling point, its ability to dissolve many substances, and its unusual behavior of expanding when it freezes all, depend on the current strength of electromagnetic forces. Change these forces, and water might become a gas at room temperature, unable to exist as a liquid in the temperature range where life can survive. But the problems would extend far beyond individual atoms and molecules. The entire process of stellar nucleosynthesis, by which stars create heavy elements from hydrogen and helium, depends critically on the current values of fundamental constants. Nuclear fusion in stellar cores converts light elements to heavier ones, but the rates of these reactions depend on both the strong nuclear force and electromagnetic interactions. The proton-proton chain, the sequence of nuclear reactions that powers the Sun and similar stars, involves a delicate balance of forces. Protons must overcome their electromagnetic repulsion to get close enough for the strong nuclear force to bind them together. This process depends on the precise strength of electromagnetic interactions. Make these interactions stronger, and fusion becomes more difficult, potentially preventing stars from igniting. Make them weaker, and fusion might proceed too rapidly, causing stars to burn out quickly. The carbon-nitrogen-oxygen cycle, which powers main sequence stars more massive than our Sun, involves a series of nuclear reactions with precisely calibrated rates. Carbon, nitrogen, and oxygen nuclei act as catalysts, facilitating the fusion of hydrogen into helium. But the rates of these reactions depend on the electromagnetic properties of the nuclei involved. Change the speed of light, and these reaction rates would shift. Stars might burn through their fuel much faster, leading to shorter stellar lifetimes, or they might burn so slowly that they never reach the temperatures needed for fusion. The triple alpha process, by which 3 helium nuclei combine to form carbon, is particularly sensitive to the values of fundamental constants. This process has an extremely narrow window of conditions under which it can occur. The energy levels involved must align almost perfectly for carbon production to be possible. The process was first explained by Fred Hoyle, who predicted the existence of a specific energy level in carbon that would make the reaction possible. This energy level depends on electromagnetic interactions between protons in the carbon nucleus. Change the speed of light, and this alignment might disappear, making it impossible for stars to create carbon at all. Without carbon production in stellar cores, the universe would remain forever dominated by hydrogen and helium. The heavy elements essential for rocky planets, atmospheric chemistry, and biological processes would never be created. The cosmic story that led from the Big Bang to planets, life, and consciousness would end abruptly in a universe of simple gases. Silicon, essential for rocky planets and the backbone of our technological civilization, is created through alpha capture processes in massive stars. These reactions depend on the electromagnetic properties of silicon nuclei and the alpha particles that bombard them. Change electromagnetic interactions, and silicon production might cease, leaving the universe without the raw materials for solid planets. Iron, the most stable nucleus and the endpoint of fusion reactions in massive stars, represents the peak of the stellar nucleosynthesis process. Stars can fuse lighter elements to create iron, releasing energy in the process. But creating elements heavier than iron requires energy input. This transition point depends on the balance between electromagnetic repulsion and nuclear binding energy. Alter the electromagnetic interactions, and this balance point might shift, changing which elements can be created through stellar fusion. Even if some nuclear reactions continued, the structure of stars themselves would be fundamentally altered. Stars exist in a state of hydrostatic equilibrium, with the outward pressure from nuclear fusion exactly balanced against the inward pull of gravity. This balance depends on the rate of fusion reactions, which depends on the electromagnetic properties of nuclei. The pressure generated by fusion reactions comes from the kinetic energy of the products and the electromagnetic radiation produced. This radiation pressure must be strong enough to support the star's mass against gravitational collapse. Change the speed of light, and this balance would shift. Stars might contract rapidly as radiation pressure decreases, leading to runaway fusion that burns through their fuel in millions rather than billions of years. Or they might expand and cool as electromagnetic interactions weaken, potentially extinguishing fusion entirely and leaving the universe filled with cold, dark stellar remnants. The main sequence, the stable phase of stellar evolution, during which stars like our Sun shine steadily for billions of years might cease to exist. Instead of the orderly progression from stellar birth to death that allows time for planets to form and life to evolve, stars might face violent, rapid changes that prevent the development of stable planetary systems. Red giant stars, the swollen phase that sun-like stars enter when they exhaust the hydrogen in their cores, depend on a delicate balance between helium fusion in the core and hydrogen fusion in a shell around the core. This balance creates the extended, cool atmospheres that characterize red giants. Change electromagnetic interactions, and this phase might not occur, or it might happen so rapidly that stars skip directly from main sequence to stellar death. Supernova explosions, which occur when massive stars exhaust their nuclear fuel and collapse catastrophically, depend on precise conditions in stellar cores. When a massive star can no longer generate enough energy to support itself against gravity, the core collapses in less than a second, rebounding in an explosion that can outshine an entire galaxy. The details of this process depend on nuclear physics, electromagnetic interactions, and the properties of matter under extreme conditions. Change the speed of light, and supernovae might not occur at all, or they might happen differently. These explosions are crucial for dispersing heavy elements throughout the galaxy, seeding future generations of stars and planets with the materials needed for complexity. Without supernovae, heavy elements would remain locked in stellar cores, unavailable for planet formation. Neutron stars, the incredibly dense remnants left behind by some supernova explosions, would face fundamental changes. These objects, with masses greater than the Sun compressed into spheres only 20 kilometers across, are held up by neutron degeneracy pressure. But the structure of neutrons and the forces between them depend on fundamental constants, including the speed of light. Neutrons themselves are composite particles made of quarks held together by the strong nuclear force. The mass of a neutron depends on the binding energy of these quarks, which involves electromagnetic interactions. Change c, and the mass and stability of neutrons might change, potentially making neutron stars impossible. The equation of state of matter at nuclear densities, which determines how neutron star material behaves under extreme pressure, depends on the interplay between the strong nuclear force and electromagnetic interactions. Alter these interactions, and neutron stars might become unstable, either collapsing into black holes or expanding into less exotic objects. Pulsars, rapidly spinning neutron stars that emit beams of electromagnetic radiation, depend on the magnetic field properties of neutron star material. These magnetic fields, among the strongest in the universe, arise from the motion of charged particles in the neutron star's interior. Change electromagnetic interactions, and pulsar behavior might change dramatically, potentially eliminating these cosmic lighthouses that serve as precise timekeepers for astronomers. White dwarf stars, the dense remnants left behind when sun-like stars exhaust their fuel, depend on electron degeneracy pressure to support themselves against gravitational collapse. This pressure emerges from quantum mechanical effects that depend on electromagnetic interactions. Change these interactions, and white dwarfs might collapse into neutron stars or black holes, dramatically altering the population of stellar remnants in the universe. The Chandrasekhar limit, the maximum mass that a white dwarf can have before collapsing, depends on the balance between gravitational attraction and electron degeneracy pressure. This limit, about 1.4 times the mass of the Sun, determines the fate of many stars. Change electromagnetic interactions, and this limit might shift, causing white dwarfs that are currently stable to collapse or allowing more massive white dwarfs to exist. Type ER supernovae, which occur when white dwarf stars accrete material from companion stars until they exceed the Chandrasekhar limit, serve as standard candles for measuring cosmic distances. These explosions have consistent brightness because they occur when white dwarfs reach a specific mass limit. Change the fundamental constants, and this limit might change. making Type Ia supernovae unreliable distance indicators and undermining our understanding of cosmic expansion. Black holes would undergo immediate and dramatic changes. The event horizon of a black hole, the boundary beyond which nothing can escape, has a radius determined by the Schwarzschild formula. This radius equals 2 times the gravitational constant times the mass divided by the speed of light squared. Change c, and every black hole in the universe would instantly change size. If the speed of light increased, black holes would shrink. Supermassive black holes at the centers of galaxies, which can contain billions of times the mass of the Sun, would suddenly have smaller event horizons. Material that was safely orbiting outside the event horizon might find itself still safely outside, but the accretion disks of hot gas spiraling into these black holes would be dramatically altered. The innermost stable circular orbit, the closest distance at which material can orbit a black hole without falling in, depends on the size of the event horizon. Shrink the black hole, and this orbit moves closer to the center, potentially disrupting the accretion disk and changing the energy output of active galactic nuclei. If the speed of light decreased, black holes would grow larger. Their event horizons would expand, potentially engulfing material that was previously in stable orbits. The supermassive black hole at the center of our own galaxy, Sagittarius A star, would suddenly pose a greater threat to nearby stars and gas clouds. The photon sphere, the radius at which light can orbit a black hole, would also change. This sphere, located at 1.5 times the Schwarzschild radius, determines the appearance of black holes when viewed from a distance. Change the speed of light, and the visual appearance of black holes would change, potentially making them easier or harder to detect. The Hawking radiation emitted by black holes would also change dramatically. Stephen Hawking showed that black holes emit thermal radiation due to quantum effects near the event horizon. The temperature of this radiation is inversely proportional to the black hole's mass and depends on the fundamental constants, including the speed of light. The temperature is proportional to the speed of light to the 4th power divided by the mass. Change c, and the rate at which black holes evaporate would change dramatically. Small black holes, if any exist, might suddenly evaporate much faster, releasing enormous amounts of energy in the process. A black hole with the mass of a mountain, which would normally take longer than the age of the universe to evaporate, might suddenly explode in a burst of gamma rays. Large black holes might effectively stop evaporating, becoming permanent features of the universe rather than objects that slowly shrink over cosmic timescales. Stellar mass black holes, which currently evaporate so slowly that the process is negligible, might become truly eternal, never returning their mass and energy to the universe. The information paradox, one of the deepest mysteries in modern physics, concerns whether information that falls into a black hole is destroyed when the black hole evaporates through Hawking radiation. This paradox depends on the precise relationship between quantum mechanics, general relativity, and thermodynamics. Change the speed of light, and this relationship might change, potentially resolving the paradox or making it even more mysterious. The cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space, would undergo fundamental changes. This radiation has been traveling through the expanding universe for over 13 billion years, and its current temperature of about 2.7 Kelvin above absolute zero depends on how the universe has expanded and cooled since the Big Bang. The energy density of electromagnetic radiation scales as the 4th power of temperature, and the relationship between energy and temperature depends on fundamental constants, including the speed of light. The energy of a photon equals Planck's constant times frequency, and frequency relates to the speed of light through the wavelength. Change c, and the cosmic microwave background might suddenly become much hotter or much cooler than its current value. If the background radiation became significantly hotter, it would interfere with the formation of stars and galaxies. Hot radiation creates pressure that opposes gravitational collapse, making it difficult for gas clouds to condense into stars. The universe might become a hot, turbulent place where structure formation is suppressed. During the epoch of recombination, when the universe was about 380,000 years old, electrons and protons combined to form neutral hydrogen for the first time. This process depends on the binding energy of hydrogen atoms, which depends on electromagnetic interactions. Change these interactions, and recombination might occur much earlier or much later in cosmic history, dramatically altering the properties of the cosmic microwave background. If the background radiation became much cooler, it would lose its current role in cosmic evolution. This radiation currently provides a heat source that affects the chemistry of interstellar gas and influences the formation of the first stars. Remove this influence, and the early universe might have evolved very differently. The acoustic oscillations in the cosmic microwave background, tiny temperature variations that reflect sound waves in the early universe, depend on the speed of sound in the primordial plasma. This speed depends on the pressure and density of the plasma, which depend on electromagnetic interactions. Change c, and these oscillations might have different wavelengths, or might not exist at all. Galaxy formation itself would be threatened. Galaxies exist because small density fluctuations in the early universe grew over billions of years through gravitational attraction. But this process depends on the balance between gravitational attraction, which tries to pull matter together, and cosmic expansion, which tries to spread it apart. The expansion rate of the universe depends on its energy content and the relationship between energy and gravity, which involves the speed of light through Einstein's field equations. The critical density that determines whether the universe expands forever or eventually collapses depends on the square of the Hubble constant divided by the gravitational constant. Since the Hubble constant has units involving the speed of light, changing CE would affect this critical density. Change C, and the expansion history of the universe would be completely different. The universe might have expanded so fast that density fluctuations never had time to grow into galaxies, leaving us with a smooth, empty cosmos. The Dark Ages, the period before the first stars formed, might have lasted forever. Alternatively, the universe might have expanded so slowly that gravity dominated early on, causing the entire universe to collapse back on itself long before stars could form. The Big Crunch, a hypothetical end to the universe where everything collapses into a single point, might have occurred billions of years ago instead of the continuing expansion we observe today. The cosmic web, the large-scale structure of the universe with its filaments of galaxies separated by vast voids, depends on the precise balance of forces and expansion rate that has characterized cosmic evolution. This structure emerged from tiny quantum fluctuations in the early universe that were stretched to cosmic scales by inflation and then grew through gravitational attraction. Change the fundamental constants, and this structure might never have formed, leaving us with a universe that is either completely smooth or collapsed into a few massive objects. The filamentary structure that connects galaxy clusters across hundreds of millions of light years might never have developed. Dark matter, the mysterious substance that outweighs ordinary matter by a factor of 5 to 1, might also be affected. While we don't yet understand what dark matter is, we know it interacts gravitationally with ordinary matter and plays a crucial role in structure formation. Dark matter particles, whatever they are, might have masses and interaction strengths that depend on fundamental constants. If the fundamental constants that govern particle physics changed, dark matter particles might decay, interact differently, or simply cease to exist. The cosmic web of dark matter that provides the scaffolding for galaxy formation might dissolve. leaving ordinary matter without the gravitational framework needed to form large-scale structures. Dark energy, the even more mysterious force that appears to be accelerating the expansion of the universe, might also respond to changes in fundamental constants. Since we understand dark energy even less than dark matter, it's impossible to predict how it might be affected, but any change could dramatically alter the future evolution of the cosmos. Dark energy currently makes up about 68% of the universe's energy density, and its properties determine whether the universe will expand forever, eventually collapse, or reach some other fate. If changing the speed of light affected dark energy, the ultimate destiny of the cosmos might be completely different from current predictions. The anthropic principle suggests that the fundamental constants of nature must have values that allow for the existence of complexity, structure, and ultimately life, simply because we exist to observe them. The fine structure constant, the ratio of proton to electron mass, the strength of the strong nuclear force, and dozens of other parameters all seem to be fine-tuned to allow for a universe that can support stars, planets, and biology. This fine-tuning is remarkable in its precision. If the strong nuclear force were just 5% weaker, deuterium would not be stable, and stars could not form helium through fusion. If it were 5% stronger, nearly all hydrogen would have been converted to helium in the Big Bang, leaving no fuel for long-lived stars. If the electromagnetic force were significantly stronger, electrons would be bound so tightly to nuclei that chemistry would be impossible. If it were much weaker, atoms would be too large and diffuse to form stable molecules. The current strength appears to be precisely calibrated to allow for the rich chemistry that makes life possible. Change the speed of light, and this fine-tuning would be destroyed. The delicate balance of forces that allows for stellar nucleosynthesis, planetary formation, and biological evolution would be upset. The universe might become a place where only the simplest structures can exist, where stars never form, where chemistry never develops beyond hydrogen and helium, where the cosmic story ends not with complexity and consciousness, but with eternal, empty darkness. The multiverse hypothesis suggests that our universe might be just one of countless others, each with different values of fundamental constants. In this view, we observe the particular values we do because we exist in one of the rare universes where these values allow for complexity and life. Most universes in the multiverse might be sterile, unable to support even the formation of atoms. But perhaps most profoundly, a universe with a different speed of light would be unknowable to us. Our entire understanding of physics, chemistry, and cosmology is based on the assumption that fundamental constants remain constant. Change C, and not only would the universe become different, our ability to understand it would disappear. We would be like children trying to read a book written in an alien language, surrounded by phenomena that follow rules we cannot even begin to comprehend. The scientific method itself depends on the assumption that the laws of nature are consistent and universal. If fundamental constants could change arbitrarily, there would be no point in conducting experiments or developing theories because the results would be unpredictable and unrepeatable. Science exists because the universe follows rules, and those rules depend on constants that remain constant. The question isn't just whether the universe would survive a change in the speed of light. The question is whether anything we would recognize as a universe, with structure, complexity, and the possibility of understanding, could exist at all. The cosmos we know may be far more fragile than we imagine, held together by the precise values of constants that we take for granted, but that may be the only values that allow anything interesting to happen in the vast darkness of space. Perhaps no aspect of reality would be more profoundly altered by a change in the speed of light than time itself. We think of time as the steady, unchanging backdrop against which all events unfold, but Einstein's theories revealed that time is intimately connected to space, matter, energy, and motion. The speed of light isn't just the rate at which photons travel, it's the fundamental constant that weaves space and time together into the unified fabric of space-time. Change C, and you don't just alter how fast things move, you rewrite the very nature of temporal experience. The most immediate and shocking change would be in the relationship between time and motion. According to special relativity, time dilation occurs whenever objects move at high speeds relative to each other. The faster you travel, the slower time passes for you compared to someone at rest. This effect depends critically on the speed of light, which serves as the cosmic speed limit and the benchmark against which all motion is measured. The time dilation factor is calculated using the Lorentz transformation, which depends on the ratio of your velocity to the speed of light. Specifically, time dilates by a factor of 1 divided by the square root of 1 minus v squared over c squared. This formula shows that as your velocity approaches the speed of light, time dilation becomes infinite, which is why nothing with mass can reach light speed. But if the speed of light suddenly changed, this entire framework would collapse and rebuild itself around a new cosmic speed limit. Imagine if c suddenly doubled overnight. Objects that were previously traveling at what seemed like modest speeds would suddenly find themselves at significant fractions of the new speed limit, experiencing time dilation effects that weren't there before. A commercial airliner traveling at 900 kilometers per hour, which experiences virtually no time dilation under current physics, would suddenly find itself traveling at a more significant fraction of the new cosmic speed limit. While the effect would still be tiny, it would be measurably larger than before. More dramatically, spacecraft that we've launched toward other planets, traveling at tens of thousands of kilometers per hour, would experience noticeably different time dilation effects. Conversely, if the speed of light were halved, objects that currently experience significant time dilation would find those effects enormously amplified. Particles in accelerators that currently approach 99% of light speed would suddenly be traveling at 198% of the new light speed, which is impossible. Something would have to give. Either the particles would be forced to slow down, or the fundamental structure of matter itself would be altered. The implications for space travel would be revolutionary and terrifying. Currently, traveling to nearby stars would require either extremely long journeys at modest speeds, or attempts to reach very high speeds where time dilation might make the journey tolerable for travelers, though centuries would pass on Earth. But change the speed of light, and all these calculations become meaningless. If c increased, interstellar travel might become more feasible. The time dilation effects that currently require enormous energies to achieve might be accessible at lower speeds. A spacecraft that could reach 10% of the old light speed might experience time dilation equivalent to what previously required 20% of light speed. But if c decreased, interstellar travel might become impossible by any conceivable technology. The energy required to reach speeds where significant time dilation occurs would increase enormously. Worse, the distances to other stars, when measured in terms of the new light travel time, would effectively double, making the universe seem even more impossibly vast. The very measurement of time would face an immediate crisis. Our current definition of the second is based on the oscillations of cesium atoms, specifically the time it takes for 9,192,631,770 oscillations of the radiation corresponding to the transition between two specific energy levels in cesium-133. But these atomic oscillations depend on electromagnetic interactions, which depend on the fine structure constant, which depends on the speed of light. Change c, and cesium atoms would oscillate at a different frequency. The atomic clocks that define our time standards would suddenly be running fast or slow compared to the new physics. This wouldn't just be a technical inconvenience requiring recalibration. It would represent a fundamental break in the continuity of time measurement. The second that existed before the change would be literally incompatible with the second that exists after. Time itself would have a discontinuity, a moment when its very definition changed. Even mechanical clocks would be affected. Pendulum clocks depend on gravity and the physical properties of their components. While gravity might not change directly with the speed of light, the electromagnetic forces that give materials their strength and elasticity would change. Clock springs might become stiffer or more flexible, affecting the rate at which mechanical timepieces run. But the changes would go far deeper than clock mechanisms. Biological time, the rhythms that govern life processes, would face disruption on every level. Every living organism operates according to biological clocks that have been calibrated by evolution to work with current electromagnetic interactions and energy scales. The biochemical reactions that power cellular metabolism depend on the precise energies of molecular bonds, which depend on electromagnetic forces. Change these forces, and the rates of these reactions would change. Enzymes that catalyze biological reactions are precisely shaped to interact with specific molecules at specific energy levels, alter the electromagnetic interactions, and these enzyme reaction rates would shift. The sodium-potassium pump, which maintains the electrical potential across cell membranes and is essential for nerve function, depends on the precise energies required to move ions against concentration gradients. Change electromagnetic interactions, and this pump might work faster, slower, or not at all. The electrical signals that travel along nerves depend on the movement of charged particles through cell membranes, processes that would be affected by changes in electromagnetic forces. DNA replication, the process by which genetic information is copied during cell division, depends on the precise timing of biochemical reactions. The enzymes that unwind the double helix, copy the genetic code, and repair errors all operate at rates determined by molecular energies. Change these energies, and DNA replication might become faster, slower, or error-prone. The cell cycle, which controls when cells divide, depends on complex networks of protein interactions and chemical signals. These networks have been fine-tuned by billions of years of evolution to operate at specific timescales. Disrupt the underlying chemistry, and cell division might become chaotic, potentially leading to cancer, like uncontrolled growth or cell death. Circadian rhythms, the approximately 24-hour cycles that regulate sleep, hormone production, and countless other biological processes, depend on molecular clocks within cells. These clocks are based on the production and degradation of specific proteins in feedback loops that take about 24 hours to complete. Change the rates of the underlying chemical reactions, and these cycles might speed up or slow down, disrupting the coordination between internal biological time and the external day-night cycle. Even more fundamentally, the aging process itself might change. Aging is caused by the accumulation of cellular damage over time, including DNA mutations, protein misfolding, and the breakdown of cellular structures. The rates of these processes depend on the energies of molecular interactions. Change electromagnetic forces, and the balance between damage and repair might shift, potentially making aging faster or slower. Photosynthesis, the process by which plants convert sunlight into chemical energy, depends on the precise energies of photons and the electronic properties of chlorophyll molecules. If the speed of light changed, the electromagnetic spectrum would shift, potentially moving sunlight out of the range that chlorophyll can efficiently absorb. Plants might suddenly find themselves unable to harvest solar energy effectively, disrupting the base of most food chains. The seasonal cycles that govern plant growth, animal migration, and ecosystem dynamics are all calibrated to the current relationship between solar energy and biological chemistry. Change this relationship, and the timing of these cycles might shift dramatically. Spring might come early or late, or the signals that trigger seasonal changes might become unrecognizable to living organisms. Human perception of time would face its own unique challenges. Our sense of time passing is partly based on the rhythm of neural oscillations in the brain, which depend on the electrical properties of nerve cells. These properties depend on electromagnetic interactions that would change if C changed. The brain waves that characterize different states of consciousness might speed up or slow down, potentially altering our subjective experience of time. The neurotransmitters that carry signals between brain cells are released and absorbed at rates determined by molecular energies. Change these energies, and the speed of thought itself might change. Memories are stored through changes in the strength of connections between neurons, processes that depend on protein synthesis and other biochemical reactions. Alter these reaction rates, and memory formation and recall might be affected. Sleep cycles, which depend on the production and breakdown of neurotransmitters, like melatonin and serotonin, might become desynchronized with the external world. The carefully orchestrated sequence of sleep stages that allows the brain to consolidate memories and restore function might be disrupted. Even our emotional responses to time might change. The feeling of anxiety often involves an overestimation of how quickly time is passing, while depression can make time feel like it's moving slowly. These subjective experiences of time depend on neural mechanisms that would be affected by changes in electromagnetic interactions. But perhaps most profoundly, the very concept of simultaneity would be rewritten. Einstein showed that there is no universal now, no moment that can be called the present throughout the universe. Whether two distant events occur simultaneously depends on the reference frame of the observer, and this relativity of simultaneity depends critically on the speed of light. The relativity of simultaneity arises from the finite speed of light, and the fact that this speed is the same for all observers. When you try to synchronize clocks at different locations, you must account for the time it takes light signals to travel between them. Change the speed of light, and the synchronization procedure changes, leading to a different definition of simultaneity. If the speed of light increased, events that were previously considered simultaneous in some reference frame might no longer be simultaneous. The careful coordination of events across space would need to be completely recalculated. Conversely, if the speed of light decreased, the relativity of simultaneity would become more pronounced, making it even more difficult to define a universal present moment. This has profound implications for causality, the relationship between cause and effect. Currently, the speed of light serves as the ultimate speed limit for the transmission of information and causal influence. An event can only affect another event if there's enough time for a light signal to travel between them. This creates a well-defined structure of cause and effect throughout space-time. Change the speed of light, and this causal structure would be redrawn. Events that were previously causally connected might become causally isolated, unable to influence each other. Conversely, events that were causally isolated might suddenly become connected, potentially creating paradoxes or contradictions in the flow of cause and effect. The light cones that define the causal structure of space-time would change shape. These cone-shaped regions determine which events can influence or be influenced by a given event. Expand or contract these cones by changing the speed of light, and you fundamentally alter the possibilities for interaction and causation throughout the universe. Time travel paradoxes, which currently require faster than light travel to create, might become possible at lower speeds if the speed of light decreased. Alternatively, if the speed of light increased, it might become even more difficult to create the closed time-like curves that could lead to paradoxes. The GPS satellites that orbit Earth must account for both special and general relativistic time effects to maintain accuracy. Special relativity causes their clocks to run slow because they're moving relative to Earth, while general relativity causes them to run fast because they're in a weaker gravitational field. These effects nearly cancel out, leaving a small net correction that must be applied. But these corrections depend on the precise value of the speed of light. Change c, and the entire GPS system would need to be recalibrated. More fundamentally, the relationships between different relativistic effects would change, potentially making it impossible to maintain synchronization across the satellite network. The age of the universe itself would become meaningless. Currently, we calculate the age of the universe based on how long light from the most distant galaxies has been traveling to reach us. This calculation assumes that the speed of light has remained constant throughout cosmic history. Change c, and this assumption becomes invalid. If the speed of light changed suddenly, we would lose our ability to interpret observations of distant galaxies. The redshift of their light, which we currently use to measure their distance and velocity, depends on assumptions about light propagation that would no longer be valid. Our entire cosmological timeline, from the Big Bang to the formation of galaxies to the evolution of the universe, would need to be reconsidered. The cosmic microwave background radiation, which provides our best evidence for the Big Bang, has been traveling toward us for over 13 billion years. But if the speed of light changed, the relationship between the age of this radiation and its current properties would be disrupted. We might suddenly receive radiation that left distant regions of the universe under completely different physical laws. Even the fundamental arrow of time, the fact that we remember the past but not the future, might be affected. This arrow emerges from the second law of thermodynamics, which states that entropy always increases over time. But the rates of thermodynamic processes depend on molecular energies and interaction rates that would change if electromagnetic forces changed. If thermodynamic processes sped up or slowed down relative to other physical processes, the arrow of time might become more or less pronounced. The distinction between past and future, which seems so fundamental to our experience, might become blurred or might be magnified in unexpected ways. The very possibility of measurement and observation depends on electromagnetic interactions. Light carries information from distant objects to our eyes and instruments, allowing us to perceive and study the world around us. Change the speed and properties of light, and our ability to observe and understand the universe would be fundamentally altered. Astronomy, which depends entirely on the analysis of electromagnetic radiation from distant objects, would face a complete revolution. The relationships between color, brightness, distance, and velocity that form the foundation of astronomical observation would all change. Spectroscopy, which allows us to determine the composition and motion of stars and galaxies, would require completely new calibrations and interpretations. Perhaps most unsettling of all, we would lose our ability to predict the future or even understand the present. Physical laws work because they allow us to calculate how systems will evolve over time. But these calculations depend on the assumption that fundamental constants remain constant. Change the speed of light, and our equations would no longer describe reality. We would be thrust into a universe where the future is not just unknown but unknowable, where the laws of physics themselves might be changing faster than we can understand them. Time, which has been humanity's most reliable companion throughout our journey from ancient civilizations to modern science, would become a stranger whose behavior we could no longer predict or comprehend. The universe we thought we understood, where time flows steadily from past to future according to comprehensible laws, would be replaced by something alien and unpredictable. We would be forced to rebuild our understanding of time from the ground up, assuming we survived long enough in this strange new temporal landscape to attempt such a reconstruction. The catastrophic change in the speed of light wouldn't occur in isolation. The fundamental constants of nature aren't independent numbers that can be adjusted one at a time, like dials on a cosmic control panel. They're interconnected through deep symmetries and relationships that bind the laws of physics into a coherent whole. Pull on the thread of the speed of light, and the entire fabric of physical law begins to unravel, potentially dragging other constants and principles down with it. To understand why changing one constant threatens all others, we need to delve into the profound interconnectedness that underlies physical reality. The constants we observe aren't arbitrary numbers chosen by chance. They emerge from the fundamental structure of space-time, the symmetries that govern particle interactions, and the mathematical relationships that make the universe comprehensible. Consider the fine structure constant, often called the most important dimensionless number in physics. This constant, approximately 1 divided by 137, determines the strength of electromagnetic interactions. But it's not an independent parameter. It emerges from a combination of 3 more fundamental quantities: the elementary charge of an electron, Planck's constant, and the speed of light. The fine structure constant equals the elementary charge squared, divided by 4 pi times the permittivity of free space times Planck's constant times the speed of light. Change C, and you immediately change this fundamental constant that governs everything from the stability of atoms to the brightness of stars. But the implications go much deeper than simple proportional scaling. The permittivity of free space, which determines how electric fields behave in vacuum, is itself related to the speed of light through Maxwell's equations. The speed of light in vacuum equals 1 divided by the square root of the permittivity times the permeability of free space. These aren't independent constants, but different aspects of the same underlying electromagnetic properties of space-time. Change the speed of light, and you must also change either the permittivity or permeability of free space, or both. But these constants appear throughout electromagnetic theory, governing the behavior of electric and magnetic fields in all circumstances. Alter them, and every electromagnetic phenomenon in the universe changes simultaneously. The relationship between electricity and magnetism, discovered by James Clerk Maxwell in the 19th century, depends critically on these constants. Maxwell's equations show that changing electric fields create magnetic fields, and changing magnetic fields create electric fields, with the speed of light determining the relationship between these two phenomena. If the speed of light changed, but the fundamental structure of electromagnetic theory remained the same, then the permittivity and permeability of free space would have to change proportionally. But these constants don't just affect empty space, they determine how electromagnetic fields interact with matter, how charges accelerate in response to forces, and how energy is stored in electric and magnetic fields. The energy density of an electric field depends on the permittivity of free space, while the energy density of a magnetic field depends on the permeability. Change these constants, and the energy stored in electromagnetic fields throughout the universe would change instantly. Capacitors would store different amounts of energy, inductors would behave differently, and the electromagnetic energy that fills space around every charged particle would shift. But the connections run even deeper. Planck's constant, which governs quantum mechanics, appears in the fine structure, constant alongside the speed of light. In the quantum world, energy and frequency are related through Planck's equation. Energy equals Planck's constant times frequency. But frequency and wavelength are related to the speed of light through the wave equation. Speed equals frequency times wavelength. These relationships form a tight web of interdependence. Change the speed of light, and you affect the relationship between energy and frequency for quantum particles. Change this relationship, and you alter the fundamental behavior of atoms, molecules, and all quantum systems. The energy levels of electrons in atoms, the frequencies of absorbed and emitted light, and the rates of quantum transitions would all shift. The uncertainty principle, one of the cornerstones of quantum mechanics, states that you cannot simultaneously know both the position and momentum of a particle with perfect precision. The mathematical expression of this principle involves Planck's constant, but it also depends on the relationship between energy and momentum, which involves the speed of light through Einstein's mass-energy relation. For massless particles like photons, energy equals momentum times the speed of light. For massive particles, the relationship is more complex, involving both the rest mass energy and the kinetic energy. Change c, and these relationships change, potentially altering the uncertainty principle itself and the fundamental limits on measurement and knowledge. The Planck units, which represent the natural scales of physics, depend on combinations of fundamental constants, including the speed of light, Planck's constant, and the gravitational constant. The Planck length, about 10 to the negative 35 meters, is the scale at which quantum effects of gravity become important. The Planck time, about 10 to the negative 43 seconds, is the shortest meaningful time interval. The Planck energy represents the scale at which particle physics and cosmology meet. These units aren't just convenient measures. They represent the fundamental granularity of space-time itself, the scales at which the smooth geometry of Einstein's relativity gives way to the foamy quantum structure of space and time. Change the speed of light, and these fundamental scales change, potentially altering the basic structure of reality at the smallest levels. The gravitational constant, which determines the strength of gravity, might seem independent of electromagnetic phenomena and the speed of light. But general relativity shows that gravity isn't really a force at all. It's the curvature of space-time caused by matter and energy. Einstein's field equations relate the curvature of space-time to the distribution of matter and energy, and these equations contain factors of the speed of light. The field equations state that the Einstein tensor, which describes space-time curvature, equals 8 pi times the gravitational constant divided by the speed of light to the 4th power, times the stress-energy tensor, which describes the distribution of matter and energy. Change c, and you change the fundamental relationship between matter and space-time curvature. This doesn't necessarily mean that the gravitational constant itself would change, but it does mean that the way gravity manifests in the universe would be different. The strength of gravitational interactions between particles, the rate at which gravitational waves propagate, and the relationship between mass and space-time curvature would all be affected. Gravitational waves, ripples in space-time itself, propagate at exactly the speed of light. These waves carry energy away from accelerating massive objects, and the rate of energy loss depends on the speed of light raised to the 5th power. Change c, and the rate at which binary pulsars lose energy to gravitational radiation would change dramatically, potentially making these systems unstable or causing them to evolve differently. The equivalence principle, which states that gravitational acceleration is indistinguishable from other forms of acceleration, depends on the precise relationship between inertial mass and gravitational mass. This relationship involves fundamental constants and could be affected by changes in the speed of light through its connections to electromagnetic and quantum phenomena. Even the strong nuclear force, which binds protons and neutrons together in atomic nuclei, might not be immune to changes in the speed of light. While the strong force itself is carried by gluons rather than photons, the particles that feel this force, quarks and gluons, also carry electric charge and are subject to electromagnetic interactions. The running of coupling constants, a quantum mechanical effect where the strength of forces changes with energy scale, involves all the fundamental forces simultaneously. The electromagnetic, weak and strong forces all affect each other through quantum corrections, and these corrections depend on the fundamental constants, including the speed of light. In grand unified theories, which attempt to describe all forces except gravity as different aspects of a single underlying force, The coupling constants of the different forces are related through symmetry-breaking mechanisms. These theories predict that at high enough energies, the electromagnetic, weak and strong forces become indistinguishable. Change one coupling constant, and the others must change to maintain the underlying symmetries. The weak nuclear force responsible for certain types of radioactive decay is already unified with electromagnetism in the electroweak theory. This unification shows that these two forces are really different aspects of the same underlying interaction, separated only by the mechanism that breaks the symmetry between them. The W and Z bosons that carry the weak force have masses determined by this symmetry breaking, and these masses depend on the fundamental constants of the electroweak theory. Change the speed of light, and you change the electromagnetic coupling constant, which would necessarily affect the weak force as well. The rates of radioactive decay, the stability of atomic nuclei, and the processes that power nuclear reactors and stars would all be affected. The Higgs mechanism, which gives mass to fundamental particles, depends on the vacuum expectation value of the Higgs field. This vacuum state represents the lowest energy configuration of the Higgs field throughout space, and its value determines the masses of particles like electrons, quarks, and the W and Z bosons. But the energy scales involved in the Higgs mechanism are related to other fundamental constants through quantum corrections and symmetry requirements. Change the speed of light, and the quantum corrections to the Higgs potential would change, potentially shifting the vacuum expectation value and altering the masses of fundamental particles. Electrons might become heavier or lighter, quarks might change mass, and the entire spectrum of particle masses that emerged from the Big Bang might be different. The cosmological constant, which describes the energy density of empty space and drives the accelerated expansion of the universe, might also be affected. This constant is related to the vacuum energy of quantum fields, and vacuum energy depends on the fundamental scales of physics through the Planck units and other combinations of constants. Current theories predict that the cosmological constant should be enormous, much larger than observed, leading to what's called the cosmological constant problem. The observed value seems to be fine-tuned to allow for the existence of galaxies and large-scale structure. Change the fundamental constants, and this delicate balance might be destroyed, leading to a universe that expands too rapidly for structure formation or contracts immediately back to a big crunch. The standard model of particle physics, our best current theory of fundamental particles and forces, contains about 25 fundamental constants whose values must be determined by experiment. These include the masses of quarks and the leptons, the coupling constants of the different forces, and parameters that describe how particles mix and transform into each other. But these constants aren't truly independent. They're connected through quantum corrections, symmetry requirements, and the consistency conditions that make the theory mathematically viable. Change one constant, and the others must adjust to maintain the theory's internal consistency, assuming the theory remains valid at all. The anthropic principle suggests that the fundamental constants must have values that allow for the existence of complexity and life, simply because we exist to observe them. Small changes in any of these constants would make atoms unstable, prevent star formation, or eliminate the chemical processes that make biology possible. This fine-tuning is remarkably precise. If the strong nuclear force were just 5% stronger, carbon would be unstable, making carbon-based life impossible. If it were 5% weaker, nuclear fusion in stars would be inefficient, preventing the creation of heavy elements. The electromagnetic force, the weak nuclear force, and even the gravitational constant all seem to be precisely calibrated to allow for a universe that can support complexity. Change the speed of light, and this entire edifice of fine-tuned constants would collapse. The delicate balance that allows for stars, planets, chemistry, and biology would be destroyed. But more than that, the mathematical consistency that makes physical theories possible would be threatened. Physical theories work because they satisfy certain mathematical requirements. They must be consistent, meaning they don't contain contradictions. They must be complete, meaning they provide definite predictions for all physical situations, and they must be invariant under certain symmetries, meaning the laws of physics look the same to different observers. These requirements place strict constraints on the possible values of fundamental constants. Change one constant arbitrarily, and the theory might become inconsistent, leading to mathematical contradictions that make physical predictions impossible. Or it might become incomplete, leaving some physical situations undefined. Or it might violate fundamental symmetries, making the laws of physics depend on arbitrary choices of reference frame. The renormalization procedure, which removes infinite quantities from quantum field theory calculations, depends on the precise relationships between fundamental constants. This procedure is what makes quantum electrodynamics and other quantum field theories mathematically sensible. Change the constants arbitrarily, and the renormalization procedure might fail, making the theory mathematically meaningless. Gauge invariance, the symmetry principle that underlies all modern theories of fundamental forces, requires that physical laws remain unchanged under certain transformations of the mathematical fields used to describe particles. This invariance places strict constraints on how different constants can be related. Violate gauge invariance, and the theory loses its predictive power and mathematical consistency. The principle of general covariance, which requires that the laws of physics look the same in all coordinate systems, is fundamental to general relativity and modern physics. This principle constrains how different physical quantities can depend on fundamental constants. Change these dependencies arbitrarily, and general covariance might be violated, undermining our understanding of space-time and gravity. But perhaps most fundamentally, the very concept of physical law depends on the assumption that fundamental constants remain constant. Laws of physics are mathematical relationships that allow us to predict how systems will behave under different conditions. These predictions only work if the parameters in the equations remain stable over time and space. If fundamental constants could change arbitrarily, there would be no point in formulating physical laws at all. Every measurement would be meaningless because the relationships between physical quantities would be constantly shifting. Science itself, as a method for understanding and predicting natural phenomena, would become impossible. The universe we inhabit isn't just one where the constants happen to have values that allow for complexity and life. It's a universe where the constants are locked in place by mathematical relationships so tight and interdependent that changing any one of them threatens to bring down the entire structure of physical law. Change the speed of light, and you don't just alter one number in a physics textbook. You potentially destroy the mathematical consistency that makes physics possible, the symmetries that give laws their universal character, and the fine-tuning that allows for the existence of anything interesting in the cosmos. The question isn't whether other fundamental constants would survive a change in the speed of light. The question is whether the concept of constant universal physical laws would survive such a change at all. We might find ourselves in a universe where nothing is constant, where physical laws themselves are as changeable and unpredictable as the weather, where the very notion of understanding through science becomes a relic of a more stable cosmic era that we can remember but never reclaim. Beyond the cosmic upheaval and technological collapse lies perhaps the most intimate question of all. What would it feel like to be human in a universe where the speed of light had changed? Our entire sensory experience, our perception of reality, and our understanding of ourselves are calibrated to the current laws of physics. Change these fundamental rules, and the very nature of human experience would be transformed in ways both subtle and profound. The most immediate change would be in how we see the world around us. Human vision depends on our ability to detect electromagnetic radiation in a narrow band of frequencies that we call visible light. This band, spanning wavelengths from about 380 to 750 nanometers, represents only a tiny fraction of the electromagnetic spectrum. But it's the range that our eyes have evolved to perceive over millions of years. But if the speed of light changed, the entire electromagnetic spectrum would shift. The relationship between frequency and wavelength would be altered, and the energies of photons at different frequencies would change. Light that appeared red before the change might suddenly become infrared, invisible to human eyes. What we perceived as blue might shift into the ultraviolet range, potentially becoming harmful rather than simply visible. The sun, our primary source of illumination, would no longer look the same. The sun's surface temperature of about 5800 Kelvin produces a characteristic spectrum of light that peaks in the yellow-green region. This is why the sun appears yellowish-white to our eyes, and why plants have evolved to be most efficient at absorbing red and blue light while reflecting green. Change the speed of light, and the relationship between temperature and the color of emitted light would shift. The sun might appear to change color dramatically, shifting toward red or blue, depending on how the electromagnetic spectrum was affected. But more than just changing color, the sun might become dimmer or brighter as the energy per photon changed, and our eyes' sensitivity to the shifted spectrum changed. The sky itself would transform. The blue color of Earth's sky comes from Rayleigh scattering, a phenomenon where shorter wavelengths of light are scattered more strongly by molecules in the atmosphere than longer wavelengths. This is why the sky is blue during the day and why sunsets are red when we see the longer wavelengths that have survived passage through more atmosphere. But Rayleigh scattering depends on the wavelength of light, and wavelengths would shift if the speed of light changed. The sky might become a completely different color, or it might become gray if the scattering properties no longer matched our visual sensitivity. Sunsets and sunrises, those daily reminders of our planet's rotation, might lose their familiar beauty or gain an alien magnificence as the colors shift beyond recognition. Plants would face a crisis that would be immediately visible to human observers. Photosynthesis depends on chlorophyll molecules that are precisely tuned to absorb red and blue light while reflecting green. This is why most plants appear green to our eyes. But if the electromagnetic spectrum shifted, chlorophyll might no longer be able to absorb the wavelengths it needs for photosynthesis. Plants might begin to change color as they either adapt to new wavelengths or begin to die from lack of usable solar energy. Forests that have been green for millions of years might turn brown, red, or even black as vegetation struggles to cope with the new electromagnetic environment. The oxygen production that has maintained Earth's atmosphere for billions of years might slow or stop entirely. The colors of everyday objects would be transformed in unpredictable ways. The red of a rose, the blue of the ocean, the golden color of wheat fields, all depend on how materials absorb and reflect specific wavelengths of light. Change the spectrum, and these familiar colors would shift. Objects might become invisible if they now absorb or reflect wavelengths outside our visual range, or they might suddenly become blindingly bright if they now reflect wavelengths to which our eyes are particularly sensitive. Human perception of depth and distance would be affected. Our ability to judge how far away objects are depends partly on atmospheric perspective, the way distant objects appear hazier and bluer due to scattering in the atmosphere. Change the scattering properties, and this depth cue would be altered. Mountains might no longer appear to fade into blue haze, making it difficult to judge distances in landscapes. The polarization of light, which some humans can faintly perceive and which many animals use for navigation, would change as electromagnetic properties shifted. Bees, which navigate using polarized light patterns in the sky, might lose their way. Birds that migrate using magnetic fields, which are related to electromagnetic phenomena, might find their navigation systems disrupted. But the changes would go far beyond vision. Human hearing depends on sound waves traveling through air at a speed determined by the properties of gas molecules. While sound speed isn't directly related to the speed of light, the electromagnetic forces that hold air molecules together and determine their behavior would be affected by changes in fundamental constants. The speed of sound in air, about 343 meters per second at room temperature, depends on the mass of air molecules and the forces between them. Change electromagnetic interactions, and the properties of nitrogen and oxygen molecules would change, potentially altering the speed of sound. Our entire auditory world, calibrated to current sound speeds, would be disrupted. The frequencies of sounds that we can hear, roughly from 20 to 20,000 hertz, represent the range that our ears have evolved to detect. But if the properties of air changed, the relationship between sound frequency and perceived pitch might change. Musical instruments, calibrated to work with current air properties and human hearing, might sound completely different or might not work at all. The human voice itself would be affected. Speech depends on the resonance properties of the vocal tract, which depend on the speed of sound in air. Change these properties, and human voices might shift in pitch or timbre. The subtle acoustic cues that allow us to recognize individual voices, detect emotions, and understand speech in noisy environments might be altered beyond recognition. The sense of touch would face its own transformation. Our ability to feel pressure, texture, temperature, and pain depends on nerve endings that respond to mechanical and thermal stimuli. But these responses depend on the electromagnetic properties of biological molecules and cell membranes. Nerve impulses travel through the body as electrical signals carried by the movement of sodium and potassium ions across cell membranes. The speed and strength of these signals depend on electromagnetic interactions that would change if fundamental constants shifted. Touch sensations might become more or less sensitive, faster or slower to develop, or might convey entirely different information about the physical world. The sense of pain, crucial for survival, depends on specialized nerve fibers that respond to potentially damaging stimuli. These pain signals travel to the brain at speeds determined by the electrical properties of nerve fibers. Change these properties, and pain responses might be delayed, amplified, or diminished, potentially making the body unable to respond appropriately to threats. Temperature sensation depends on how heat energy affects specialized receptor molecules in nerve endings. But the relationship between thermal energy and molecular motion depends on electromagnetic interactions. Change these interactions, and our perception of hot and cold might shift, making previously comfortable temperatures feel painful, or making dangerous temperatures feel comfortable. The sense of smell would face perhaps the most dramatic changes. Olfaction depends on the binding of odor molecules to receptor proteins in the nose, and this binding depends on the precise shapes and electromagnetic properties of both the molecules and the receptors. Change electromagnetic interactions, and the lock and key relationship between odors and receptors would be disrupted. Familiar smells might become undetectable, while previously odorless substances might suddenly have strong scents. The rose might lose its fragrance, while the air itself might develop strange new odors, as molecules interact differently with our olfactory receptors. The complex world of human smell, which influences everything from appetite to emotional memories, would be fundamentally altered. Taste would undergo similar disruption. The 5 basic tastes, sweet, sour, salty, bitter, and umami, depend on specific interactions between food molecules and taste receptor cells on the tongue. These interactions involve electromagnetic forces that would change if fundamental constants shifted. Foods might lose their familiar flavors or develop entirely new tastes that humans have never experienced. The human brain itself would face unprecedented challenges. Neural computation depends on the precise timing of electrical signals traveling through networks of interconnected neurons. The speed of these signals depends on the electrical properties of nerve cell membranes and the concentrations of ions inside and outside cells. Change electromagnetic interactions, and neural signals might travel faster or slower, potentially disrupting the carefully timed processes that underlie thought, memory, and consciousness. The brain's ability to integrate information from different sensory systems, to form memories, and to coordinate complex behaviors all depend on precise timing relationships that could be destroyed by changes in fundamental physics. Memory formation involves changes in the strength of connections between neurons, a process that depends on protein synthesis and other biochemical reactions. Alter the rates of these reactions by changing electromagnetic interactions, and memory might become more or less durable, faster or slower to form, or might fail entirely. Sleep, that mysterious state that occupies a third of human life, depends on complex changes in brain chemistry and neural activity. The neurotransmitters that regulate sleep and wakefulness, the brain waves that characterize different sleep stages, and the biological clocks that determine when we feel sleepy all depend on electromagnetic interactions between molecules. Change these interactions and human sleep patterns might be completely disrupted. People might find themselves unable to sleep, unable to wake up, or cycling through sleep and wake states on completely different schedules than the 24-hour day. The crucial functions that sleep serves, from memory consolidation to cellular repair, might be compromised. Dreams, those strange altered states of consciousness that occur during sleep, depend on patterns of neural activity that involve precise electrochemical processes. Change electromagnetic interactions, and the very nature of dreaming might be altered. People might experience more vivid dreams, no dreams at all, or forms of dream consciousness that are completely unlike anything humans have previously experienced. Human emotions would not be immune to these changes. Emotions involve complex interactions between neurotransmitters, hormones, and neural circuits, all of which depend on electromagnetic processes. The chemical signals that produce feelings of happiness, sadness, fear, or love might be altered in ways that change the fundamental nature of human emotional experience. Depression and anxiety, mental health conditions that affect millions of people, involve imbalances in neurotransmitter systems. Change the underlying electromagnetic interactions, and these conditions might become more or less common, might manifest with different symptoms, or might require entirely different treatments. The placebo effect, where the mere belief that a treatment will work can produce real physiological changes, depends on complex interactions between mind and body that involve neural and hormonal systems. These systems might respond differently to belief and expectation if their underlying chemistry changed. Human reproduction would face fundamental challenges. The hormonal cycles that regulate fertility, the biochemical processes involved in pregnancy, and the development of embryos and fetuses all depend on precisely calibrated molecular interactions. Change electromagnetic forces, and human reproduction might become more difficult, less reliable, or might fail entirely. The development of human embryos follows a precise genetic program that depends on the timing of gene expression and protein production. Alter the rates of these processes, and embryonic development might be disrupted, potentially leading to birth defects or developmental failures that prevent normal human reproduction. Even human aging might proceed differently. The cellular damage that accumulates over time and leads to aging involves interactions between molecules that depend on electromagnetic forces. Change these forces, and the balance between cellular damage and repair might shift, potentially making humans age faster or slower than before. The immune system, which protects the body from disease, depends on complex recognition processes where immune cells identify foreign substances based on their molecular structures. These recognition processes involve electromagnetic interactions between molecules. Change these interactions, and the immune system might become less effective at fighting disease or might begin attacking the body's own tissues. Human communication would face unprecedented challenges. Language itself might become problematic if changes in vocal tract properties, hearing sensitivity, or neural processing speeds affected our ability to produce and understand speech. The subtle acoustic cues that distinguish different words, the rhythms and inflections that convey meaning beyond the literal content of words, might all be altered. Written communication might remain more stable, but even reading depends on visual perception systems that would be affected by changes in electromagnetic radiation. The contrast between black ink and white paper, the fine details that distinguish different letters, and the visual processing that allows rapid reading might all be compromised. Human creativity, one of our species' most distinctive characteristics, emerges from complex neural processes that involve both logical reasoning and intuitive leaps. These processes depend on the precise timing and coordination of neural networks throughout the brain. Disrupt these networks by changing their underlying electrochemical properties, and human creativity might be diminished or might take entirely new forms. Art, music, literature, and science all depend on human perception and cognition working in specific ways. Change the fundamental basis of perception and cognition, and these human achievements might become impossible to create or appreciate. A Beethoven symphony might become meaningless noise if auditory processing changed. A Van Gogh painting might become invisible if visual perception shifted. The mathematical insights that drive scientific progress might become inaccessible if logical reasoning processes were disrupted. The very sense of being human, of existing as a conscious entity in a comprehensible universe, depends on the consistency of perceptual and cognitive processes that have been shaped by millions of years of evolution under current physical laws. Change these laws, and the continuity of human experience might be broken. People might find themselves trapped in bodies that no longer respond as expected, in a world that no longer looks, sounds, smells, or feels familiar, with minds that no longer process information in recognizable ways. The fundamental assumption that underlies human psychology, that the world is stable and predictable enough to be understood and navigated, would be shattered. The philosophical implications would be staggering. Human concepts of beauty, truth, meaning, and purpose have all been shaped by our evolution under current physical laws. These concepts might become meaningless in a universe where the fundamental rules have changed. The great questions that have driven human philosophy for millennia about the nature of reality, consciousness, and existence might require completely new answers, or might become unanswerable. The social structures that organize human civilization depend on shared perceptions and experiences. If individual humans began experiencing reality in fundamentally different ways, the common ground that makes communication and cooperation possible might disappear. Society itself might fragment as people found themselves unable to share a common understanding of the world around them. Perhaps most tragically, the accumulated knowledge and wisdom of human civilization might become useless overnight. The scientific understanding that has taken centuries to develop, the artistic traditions that have been passed down through generations, the practical knowledge that allows us to survive and thrive, all depend on the assumption that the physical world works according to stable, comprehensible laws. In a universe where the speed of light had changed, taking other fundamental constants with it, humans would find themselves starting over from scratch, struggling to understand a reality that follows rules no one has ever encountered before. We would be like children again, but children without the benefit of parents who understand the world well enough to guide and protect them. The question isn't just whether humanity would survive such a change in the fundamental nature of reality. The question is whether anything we would recognize as human experience, human consciousness, or human civilization could exist in such a radically altered universe, we might find ourselves becoming something else entirely, something that we cannot now imagine or comprehend, shaped by physical laws so alien that they would create forms of existence as different from current humanity as we are from the first single-celled organisms that emerged in Earth's ancient oceans. In the aftermath of such a cosmic catastrophe, assuming humanity somehow survived the collapse of physics, technology, and perception itself, we would face the monumental challenge of rebuilding our understanding of reality from the ground up. The scientific method that has served us for centuries would need to be fundamentally reconsidered, and the very concepts of measurement, experimentation, and natural law would require redefinition in a universe operating under alien rules. The first and most immediate challenge would be measurement itself. Science depends on our ability to quantify the world around us, to assign numbers to physical phenomena in ways that are consistent and reproducible. But every measurement standard we've developed assumes that fundamental constants remain constant. The meter is defined in terms of the distance light travels in a specific fraction of a second. The second is defined by atomic oscillations. The kilogram is now defined using Planck's constant and the speed of light. With the speed of light changed, these definitions would become meaningless. We would need to establish entirely new measurement standards based on whatever physical phenomena remain stable in the new universe. This wouldn't be a simple matter of recalibration. It would require identifying which physical relationships, if any, could serve as reliable references in a world where the most fundamental constants had shifted. The process might take decades or centuries. Early scientists would need to rediscover basic relationships like the connection between distance and time, the behavior of falling objects, and the properties of simple materials. They would be working without the benefit of precise instruments, since all our measurement devices were calibrated to the old physics and would no longer function reliably. Imagine trying to measure the new speed of light without atomic clocks, laser interferometers, or any of the sophisticated tools that modern physics takes for granted. Scientists would need to return to methods similar to those used by Galileo and Newton, making crude measurements with simple mechanical devices and gradually building up more sophisticated techniques as their understanding improved. The rediscovery of basic physical laws would be particularly challenging, because scientists would know that the old laws no longer applied, but they wouldn't know which aspects of those laws were universal principles and which were specific to the old values of fundamental constants. Newton's laws of motion might still be valid in some form, but the precise relationships between force, mass, and acceleration might have changed if the electromagnetic forces that give objects their mass and rigidity had shifted. The electromagnetic force itself would need to be completely recharacterized. Maxwell's equations, which have successfully described electromagnetic phenomena for over a century, would require modification to account for the new speed of light and the altered permittivity and permeability of free space. Scientists would need to rediscover the relationships between electric and magnetic fields, the behavior of charged particles, and the properties of electromagnetic radiation. This process would be complicated by the fact that all the tools used to study electromagnetism, from simple compasses to sophisticated particle accelerators, would behave differently than before. The magnetic field of Earth itself might have changed if the core's electromagnetic properties were affected. The behavior of magnets, the flow of electric current, and the generation of electromagnetic waves would all need to be studied afresh. Atomic theory would require complete reconstruction. The periodic table, one of science's greatest organizational achievements, would be obsolete. Each element would have different properties as electron energy levels shifted and chemical bonding changed. Scientists would need to rediscover which substances were elements and which were compounds, how atoms combined to form molecules, and what chemical reactions were possible under the new physics. The very concept of atomic number might need revision if the balance between electromagnetic and nuclear forces had shifted significantly. Elements that were stable under the old physics might decay rapidly, while new stable configurations might be possible. The entire science of chemistry would need to be rebuilt from first principles. Nuclear physics would face similar challenges. The strong and weak nuclear forces might have been affected by changes in fundamental constants, altering the stability of atomic nuclei and the rates of radioactive decay. The nuclear reactions that power stars and nuclear reactors would proceed at different rates, if they proceeded at all. Scientists would need to rediscover which isotopes were stable, how nuclear fission and fusion worked, and what nuclear reactions could be harnessed for energy. Quantum mechanics, the theory that describes the behavior of atoms and subatomic particles, would require fundamental revision. The uncertainty principle, wave-particle duality, and the probabilistic nature of quantum measurements all depend on the precise values of fundamental constants. Change these constants, and the quantum world might behave in completely unexpected ways. Scientists would need to rediscover the quantum nature of matter and energy, but they would be doing so without the benefit of the mathematical framework that took decades to develop in the early 20th century. The Schrödinger equation, which describes how quantum systems evolve over time, contains fundamental constants that would have new values. Even if the equation itself remained valid, all of its solutions would be different. The challenge would be particularly acute because quantum effects are typically very small and require sophisticated equipment to observe. Without functioning particle accelerators, electron microscopes, or quantum electronics, scientists would need to find new ways to probe the quantum world and develop new theoretical frameworks to describe their observations. Relativity theory would face its own crisis. Einstein's special relativity is built around the constancy of the speed of light and would need to be reformulated for the new cosmic speed limit. General relativity relates gravity to the curvature of space-time through equations that contain the speed of light, and these equations would need modification. The relationship between mass and energy, expressed in the famous equation E equals mc squared, would have a different proportionality constant. Nuclear energy, stellar energy, and the binding energy of atoms would all scale differently. Scientists would need to rediscover these relationships and understand their implications for everything from nuclear reactors to stellar evolution. Perhaps most challenging of all would be the rediscovery of cosmology. Our current understanding of the universe's origin, evolution, and structure depends entirely on observations made with electromagnetic radiation traveling at the current speed of light. In a universe where C had changed, all astronomical observations would need reinterpretation. The cosmic microwave background radiation, if it still existed, would have different properties. The relationships between stellar brightness, color, and distance would be altered. The Hubble constant, which describes the expansion of the universe, would need recalibration using the new speed of light. The entire cosmic distance ladder, the series of measurement techniques that allow us to determine distances to faraway galaxies, would collapse. Scientists would essentially be starting cosmology over from scratch, trying to understand a universe that had evolved under different physical laws than those that shaped its early history. They would be like archaeologists trying to understand an ancient civilization, but with all the artifacts suddenly transformed into unrecognizable forms. The development of new technologies would present both obstacles and opportunities. On one hand, all existing technology would be obsolete, forcing humanity to rebuild from the most basic level. Electronic devices wouldn't work, mechanical systems might behave unpredictably, and materials might have completely different properties. But on the other hand, the new physics might enable technologies that were impossible under the old laws. If the speed of light were higher, for example, it might become easier to approach significant fractions of this new speed limit, potentially making interstellar travel more feasible. if electromagnetic interactions were stronger or weaker, new forms of energy storage or manipulation might become possible. The development of new scientific instruments would be crucial but extraordinarily difficult. Scientists would need to create new devices to measure the new physical properties of the universe, but they would be doing so without understanding exactly what those properties were. It would be a bootstrap process where each new measurement capability would enable slightly more sophisticated experiments, gradually building up the knowledge needed for more advanced instruments. Communication would be a critical challenge for the scientific community. If electromagnetic radiation behaved differently, radio communications might not work as expected. The internet and other communication networks would be down. Scientists would need to find new ways to share information and coordinate research across distances. This might force a return to older forms of scientific communication, with written correspondence and face-to-face meetings becoming primary means of sharing discoveries. The rapid pace of modern scientific advancement, enabled by instant global communication, would slow dramatically as scientists struggled to maintain contact with colleagues around the world. The challenge of scientific education would be immense. All existing textbooks, research papers, and educational materials would be obsolete. Teachers would need to learn the new physics alongside their students. Universities would need to completely restructure their curricula around whatever new understanding emerged from post-catastrophe research. The very concept of scientific authority would be undermined. The experts who understood the old physics might not be the best qualified to understand the new physics. Young researchers, unencumbered by deep knowledge of the old laws, might prove more adaptable to the new reality. The scientific establishment would need to be rebuilt along with scientific knowledge itself. Funding for science would become both more critical and more difficult to obtain. Governments and institutions struggling to maintain basic infrastructure and address immediate survival needs might have little resources to spare for basic research. Yet understanding the new physics would be essential for rebuilding technological civilization. Scientists would need to demonstrate the practical value of their research more directly than ever before. The luxury of pure research, disconnected from immediate applications, might not be affordable in a world struggling to adapt to new physical laws. This could bias research toward applied problems and slow the development of fundamental understanding. The psychological challenges facing scientists would be enormous. Researchers who had spent decades mastering the old physics would see their life's work become obsolete overnight. The mental models and intuitions that guided their thinking would become worse than useless. They would become actively misleading. Young scientists might adapt more easily, but they would lack the deep experience and hard-won insights that normally guide research. The scientific community would lose generations of accumulated wisdom about how to approach difficult problems, how to design experiments, and how to interpret unexpected results. The peer review process, which ensures the quality of scientific research, would face its own crisis. With all existing knowledge obsolete, how would scientists evaluate new claims about the nature of reality? What standards of evidence would apply when no one understood the underlying principles well enough to make confident predictions? Scientific publishing would need to be rebuilt from scratch. Journals that had specialized in particular areas of physics would find their focus areas completely transformed. New publication venues would need to emerge to handle research in areas that didn't exist under the old physics. The relationship between science and society would be fundamentally altered. Public trust in science, already fragile in some quarters, might be severely damaged by the spectacular failure of scientific predictions and technological systems. Scientists would need to rebuild credibility while simultaneously acknowledging the limitations of their knowledge. Yet this crisis might also represent an unprecedented opportunity for scientific advancement. The chance to observe a universe operating under completely new physical laws would provide insights that could never be obtained under normal circumstances. scientists would have the unique opportunity to compare two different sets of natural laws, potentially revealing deep truths about the nature of physical reality that would otherwise remain hidden. The process of rediscovering physics might proceed much faster than the original development of scientific knowledge, since scientists would retain some understanding of mathematical techniques and experimental methods, even if their specific applications needed reinvention. The scientific method itself, the process of forming hypotheses and testing them through controlled experiments, would remain valid, even if all specific scientific knowledge became obsolete. New theoretical frameworks might emerge that were more elegant or comprehensive than the old ones. The crisis might force scientists to develop new mathematical tools and conceptual approaches that would represent genuine advances over pre-change science. The new physics might reveal symmetries and relationships that were hidden in the old universe. The challenge of engineering new technologies based on altered physical laws might drive innovations that would have been impossible under the old physics. Materials with properties that violate our current understanding might become possible. Energy sources that seemed forbidden by conservation laws might become accessible. Forms of computation that transcend current limitations might be discovered. Perhaps most importantly, the experience of seeing physical laws themselves change would force a fundamental reconsideration of what science is and what it can achieve. The assumption that natural laws are eternal and universal would be shattered, replaced by a more humble recognition that even the most fundamental principles might be contingent rather than absolute. This could lead to new approaches to scientific research that are more robust against future changes in physical laws. Scientists might focus more on understanding the meta-principles that determine which physical laws are possible, rather than simply cataloguing the laws that happen to apply in our particular cosmic epoch. The search for truth would continue, but it would be a search informed by the hard-won knowledge that truth itself might be more complex and changeable than anyone had previously imagined. Science would survive, but it would emerge from the crisis transformed, more humble, yet perhaps ultimately more powerful than before, armed with the knowledge that reality itself can be far stranger and more mutable than we ever dared to believe. As we reach the end of our journey through this impossible scenario, we find ourselves standing under alien skies in a universe that has been fundamentally rewritten. The familiar blue heavens have shifted to strange new hues. The sun burns with an unfamiliar light, and the very air around us carries sounds that follow rules we no longer understand. This is what remains after the speed of light, that most fundamental constant decided to change overnight. We began this exploration with a simple question: what if the speed of light changed? What started as a thought experiment in physics has revealed itself to be something far more profound. We discovered that we weren't just asking about one number in one equation. We were asking about the very foundations of existence itself, the delicate architecture of reality that makes everything from atoms to galaxies, from consciousness to civilization, possible. The speed of light, we learned, isn't simply about how fast photons travel through space. It's the thread that weaves together space and time into the unified fabric of space-time. It's the cosmic speed limit that ensures cause precedes effect. It's the conversion factor between mass and energy that powers the stars and makes chemistry possible. It's embedded in the structure of atoms, the behavior of gravity, and the expansion of the universe itself. Change this one constant, and the cascade of consequences spreads through every aspect of reality like cracks spreading through glass. Physics collapses first, as the equations that describe electromagnetic forces, quantum mechanics, and relativity all contain factors of C that suddenly have the wrong values. Technology follows immediately, as every device from atomic clocks to smartphones depends on electromagnetic properties that are no longer what their designers expected. But the devastation runs deeper than failed machines and broken theories. the very elements that make up our world would face an existential crisis. Carbon might lose its ability to form the complex molecules that make life possible. Water might no longer have the unique properties that make it the universal solvent for biology. DNA might unravel as the electromagnetic forces that hold the double helix together weaken or strengthen beyond the narrow range that allows for stable genetic information. Stars, those cosmic furnaces that have illuminated the universe for billions of years, would find their fusion reactions disrupted. The delicate balance between gravitational collapse and radiation pressure that has kept the sun shining steadily for 4.5 billion years would be destroyed. Our star might expand into a red giant, contract into a white dwarf, or undergo some completely unpredictable transformation as the new physics rewrites the rules of stellar evolution. Even time itself would become unreliable. The steady progression from past to future that provides the backdrop for all experience would be disrupted as relativity breaks down and rebuilds itself around a new cosmic speed limit. The simultaneity of distant events, the synchronization of clocks, and the very measurement of duration would all require redefinition in a universe where light travels at a different speed. Human experience would be transformed beyond recognition. Our senses, evolved over millions of years to navigate a world governed by current physical laws, would find themselves adrift in an alien reality. Colors would shift as the electromagnetic spectrum reorganized itself. Sounds would change as the properties of air molecules altered. The sense of touch, taste, and smell would all be disrupted as the molecular interactions they depend on followed new rules. Perhaps most tragically, the accumulated knowledge and wisdom of human civilization would become obsolete overnight. The scientific understanding that has taken centuries to develop, the technologies that have revolutionized human life, the artistic and cultural achievements that define our species, all depend on the assumption that the physical world operates according to stable, comprehensible laws. Yet our exploration has also revealed something remarkable about the nature of scientific inquiry itself. Even in the face of such cosmic upheaval, the human drive to understand would persist. Scientists would begin the enormous task of rebuilding knowledge from scratch, rediscovering the new laws that govern the transformed universe. The scientific method, that systematic approach to understanding through observation and experiment, would remain valid even if all specific scientific knowledge became obsolete. This imaginary catastrophe serves as a powerful reminder of how precarious our existence really is. We live in a universe balanced on a knife's edge, where tiny changes in fundamental constants could make stars impossible, atoms unstable, or consciousness itself an impossibility. The anthropic principle suggests that we observe the particular values of physical constants that we do precisely because we exist, because we live in one of the rare universes where these values allow for complexity, structure, and life. The fine-tuning required for our existence is breathtakingly precise. If the strong nuclear force were just 5% stronger or weaker, carbon production in stars would be impossible. If the electromagnetic force had a significantly different strength, chemistry as we know it couldn't exist. If gravity were much stronger or weaker, stars and planets couldn't form. We exist in a cosmic sweet spot where all the fundamental forces have exactly the right strengths to allow for the rich tapestry of phenomena we observe. This realization should fill us with both humility and wonder. Humility because it shows how dependent we are on physical laws that we don't fully understand and certainly don't control. Wonder because it reveals that we live in a universe of extraordinary beauty and complexity, where the interplay of fundamental forces has somehow given rise to stars and planets, to chemistry and biology, to consciousness and civilization. Our thought experiment also highlights the deep interconnectedness of all physical phenomena. We began by changing one constant, but we discovered that no constant exists in isolation. Each fundamental parameter is connected to others through mathematical relationships, symmetry principles, and the requirement that physical theories be logically consistent. Pull on one thread, and the entire fabric of physical law begins to unravel. This interconnectedness extends beyond physics to encompass all of human knowledge and experience. Science, technology, art, philosophy, and everyday life are all built on the foundation of physical law. Change that foundation, and everything built upon it must be reconstructed or abandoned. But perhaps the most profound lesson of our journey is about the nature of understanding itself. Human consciousness, with its ability to comprehend mathematical relationships, to perceive beauty in the cosmos, and to imagine scenarios that transcend immediate experience, represents one of the most remarkable phenomena in the known universe. The fact that matter can organize itself into patterns complex enough to contemplate the universe that created it is perhaps the greatest mystery of all. Our ability to imagine what would happen if the speed of light changed, to trace the consequences through physics and chemistry and biology, to envision the collapse and rebuilding of civilization, demonstrates the extraordinary power of human thought. We can transcend the immediate constraints of our existence to explore realms of possibility that extend far beyond our direct experience. This capacity for imagination and understanding carries with it both great power and great responsibility. Our growing knowledge of the universe gives us unprecedented ability to shape our future, but it also reveals how fragile that future might be. The same scientific understanding that allows us to imagine cosmic catastrophes also warns us about more immediate threats to human survival, from climate change to nuclear weapons to potential impacts from asteroids. As we stand under these imaginary alien skies, watching a transformed sun set through an atmosphere that follows unfamiliar rules, we're reminded that the universe we actually inhabit is far more precious than we usually appreciate. The stable laws of physics that we take for granted, the reliable behavior of matter and energy that makes prediction possible, the fine-tuned constants that allow for complexity and consciousness. These are gifts of extraordinary value. The universe doesn't owe us stability. Physical laws don't have to be comprehensible to human minds. The fundamental constants don't have to have values that permit the existence of life. Yet somehow, against astronomical odds, we find ourselves in a cosmos where all these unlikely conditions are met. Perhaps the greatest tragedy of changing the speed of light wouldn't be the collapse of physics or technology, or even civilization. Perhaps it would be the loss of our ability to appreciate the remarkable universe we actually live in. In struggling to understand a reality governed by alien laws, we might lose sight of the extraordinary beauty and elegance of the natural world as it actually exists. Our journey through this impossible scenario should leave us with a renewed sense of appreciation for the actual universe, with its stable constants and comprehensible laws. Every sunset that follows familiar physical principles, every chemical reaction that proceeds at predictable rates, every star that shines according to well-understood nuclear processes, represents a small miracle of cosmic consistency. The speed of light, racing through space at exactly 299,792,458 meters per second, carries more than just energy and information. It carries the guarantee that cause will follow effect, that space and time will remain woven together, that the universe will continue to operate according to rules we can hope to understand. In the end, our exploration of what would happen if the speed of light changed reveals something profound about the universe we actually inhabit. We live in a cosmos that is simultaneously robust enough to support billions of years of stable evolution and delicate enough that small changes in fundamental parameters could destroy everything we know and love. This knowledge should inspire us to cherish the remarkable stability that has allowed stars to shine, planets to form, life to evolve, and consciousness to emerge. It should motivate us to use our growing understanding of the universe wisely, to protect the fragile conditions that make human civilization possible, and to continue the ancient human quest to comprehend the cosmos that gave birth to us. Under familiar skies, with the speed of light exactly what it should be, we can look up at the stars and know that we are part of something vast and wonderful, and more finely tuned than any machine humans have ever built. The universe doesn't promise us permanence, but it has given us the precious gift of existence in a reality governed by laws beautiful enough to inspire wonder and stable enough to reward understanding. That may be the most remarkable discovery of all. Not what would happen if the fundamental constants changed, but what an extraordinary privilege it is to live in a universe where they remain exactly as they are.